There is a point where history stops feeling like a record and starts feeling like a gap, not a missing piece, but something deliberately removed. Across ancient remnants, we find the same unsettling patterns: precision without explanation, knowledge without origin, and structures that seem to follow rules we no longer understand. It's as if an entire layer of human understanding has been erased, leaving only echoes behind. The question is not just how these things were built, but why they were built the way they were. Because hidden within their design may be something more than function, something intentional. And if that's true, then perhaps the greatest mystery isn't what ancient civilizations created, but what they were trying to tell us. The Antikythera mechanism is widely regarded as one of the most astonishing technological discoveries from the ancient world. Recovered in 1901 from a Roman shipwreck near the Greek island of Antikythera, the device initially appeared to be nothing more than a corroded lump of bronze fragments embedded in mineral deposits. However, as archaeologists and historians began examining the artifact more closely, they realized that hidden within the fragments was something extraordinary, a complex mechanical device built more than 2,000 years ago, around the 2nd century BCE. Today, the Antikythera mechanism is often described as the world's first analog computer, a machine designed to predict astronomical events and model the motions of celestial bodies. Its existence has forced scholars to reconsider what ancient civilizations were truly capable of in terms of engineering, mathematics, and scientific knowledge. The discovery itself was accidental, made by sponge divers who had stumbled upon the remains of a large merchant ship resting on the seabed. Among statues, ceramics, and luxury goods intended for the Roman elite, the divers recovered a group of bronze fragments that would eventually puzzle researchers for more than 100 years. At first, the pieces seemed insignificant compared with the spectacular sculptures also found at the wreck site. But over time, scientists realized that these corroded fragments once formed a remarkable mechanical instrument, unlike anything else known from antiquity. When researchers began studying the internal structure of the mechanism, they discovered that it contained an intricate system of interlocking bronze gears mounted inside a wooden case, roughly the size of a shoebox. Turning a small hand crank would cause these gears to rotate in carefully coordinated patterns, driving several circular dials on the front and back of the device. These dials displayed astronomical information, including the position of the sun and the moon in the zodiac, the phases of the moon, and the timing of eclipses. Some dials even tracked long astronomical cycles lasting many years, allowing the user to predict celestial events far into the future. The mechanism effectively translated complex astronomical theories into mechanical motion, turning mathematical knowledge into a physical model of the cosmos. Yet what makes the Antikythera mechanism truly extraordinary is not simply its purpose, but the technological sophistication required to build it. The device contained dozens of bronze gears. More than 30 have been identified in surviving fragments, each cut with precise triangular teeth and arranged in elaborate gear trains designed to represent specific astronomical ratios. The existence of such a system in a device from the 2nd century BCE stunned historians, because machines with comparable mechanical complexity were previously believed to have appeared more than 1,000 years later during the medieval development of mechanical clocks. The most mysterious and impressive aspect of the Antikythera mechanism lies in the extraordinary precision of its gear-cutting technology. The bronze gears inside the device were manufactured with remarkable accuracy, featuring evenly spaced teeth that that mesh smoothly with neighboring gears. Each gear was carefully designed with a specific number of teeth to reproduce astronomical cycles using mechanical ratios. For example, some gear trains replicate the Metonic cycle, a 19-year period used by ancient astronomers to synchronize lunar and solar calendars. Others represent the Saros cycle, which predicts the recurrence of solar and lunar eclipses approximately every 18 years and 11 days. Achieving this level of mechanical sophistication required not only deep astronomical knowledge, but also exceptional skill in metalworking and precision engineering. And scholars examining the fragments have noted that the gears were cut from thin bronze plates and shaped with such uniformity that they rival components found in much later mechanical devices. This raises a profound historical question. How did ancient craftsmen produce gears with such precision using the tools available at the time? There is little evidence that advanced gear-cutting machines or specialized metalworking lathes existed in the Hellenistic world. Most surviving descriptions of ancient tools suggest relatively simple hand tools, such as chisels, files, and drills. Yet the Antikythera mechanism demonstrates a level of mechanical craftsmanship that appears to demand far more sophisticated techniques. And modern engineers who have reconstructed the mechanism using digital imaging and three-dimensional modeling often express amazement at the complexity of its design. Some of the gears are arranged in compound systems where several gears share the same axis, transmitting motion through multiple layers of mechanical relationships. Even more astonishing is the presence of what appears to be an early form of differential gearing, a system capable of combining rotational motions to produce new mechanical outputs. Differential gears are commonly associated with modern machinery, such as automobiles, and were historically believed to have been invented many centuries later. The presence of such a concept within the Antikythera mechanism suggests that ancient Greek engineers possessed a theoretical understanding of mechanical systems far more advanced than previously assumed. The accuracy of the gear ratios also indicates that the designers had access to detailed astronomical calculations, likely derived from the sophisticated mathematical traditions of Hellenistic science. Figures such as Hipparchus, the great Greek astronomer who studied lunar motion and developed precise astronomical models, are often mentioned as possible influences behind the mechanism's design. Some historians even speculate that the intellectual environment surrounding mathematicians like Archimedes may have inspired similar mechanical devices, though no direct evidence survives to confirm these theories. Another fascinating feature of the Antikythera mechanism is the presence of extensive inscriptions engraved on its bronze surfaces. Using advanced X-ray tomography and imaging techniques, researchers have identified thousands of Greek characters etched into the plates of the device. These inscriptions appear to function as explanatory labels or operating instructions, describing the astronomical cycles displayed by the dials and guiding the user in interpreting the instrument's predictions. The level of detail found in these inscriptions indicates that the mechanism was not merely an experimental prototype, but a carefully designed scientific instrument intended for practical use. It may have been used by scholars, educators, or navigators to demonstrate celestial movements and forecast astronomical events. Some researchers believe it could also have played a role in regulating calendars or predicting dates for important festivals connected to lunar cycles. Despite more than a century of study, however, the Antikythera mechanism continues to raise profound questions about the history of technology. Perhaps the most puzzling mystery is why devices of comparable complexity do not appear again for over 1,000 years. After the era of the Antikythera mechanism, the historical record becomes almost silent regarding intricate mechanical gear systems. Only during the late medieval period, with the emergence of large astronomical clocks in European cathedrals, do machines of similar mechanical sophistication reappear. This gap has led some historians to propose that the knowledge required to build such mechanisms was once more widespread in the Hellenistic world, but was later lost due to political upheavals, economic decline, or the gradual disappearance of specialized craftsmanship. If this is true, the Antikythera mechanism might represent the surviving fragment of an entire tradition of advanced mechanical engineering that vanished from history. Even today, scientists are still uncovering new details about the device. Modern scanning technologies continue to reveal hidden inscriptions and previously unknown gear arrangements buried within the corroded fragments. Some researchers suspect that the original mechanism may have contained additional components that are now missing, and potentially including displays for the motions of the 5 known planets of antiquity: Mercury, Venus, Mars, Jupiter, and Saturn. If this hypothesis proves correct, the Antikythera mechanism would represent not only a lunar and solar calculator, but a complete mechanical model of the ancient Greek understanding of the cosmos. Such a possibility only deepens the sense of wonder surrounding the device. More than 2,000 years after its creation, the Antikythera mechanism remains one of the most enigmatic artifacts ever discovered. It stands as a powerful reminder that the technological achievements of ancient civilizations may have been far more advanced and far more fragile than we once imagined. Where are you watching this video from, and what time of day is it for you? Share your location and time in the comments below. Roman glass nanotechnology, most famously demonstrated by the remarkable Lycurgus cup, stands as one of the most intriguing technological puzzles from the ancient world. Crafted during the 4th century CE within the vast territories of the Roman Empire, the cup appears at first glance to be simply an exquisite example of Roman luxury glassware. Yet careful observation reveals a phenomenon that seems almost impossible for its time. The cup changes color dramatically depending on how light interacts with it. When illuminated from the front, the glass appears a rich, opaque green. However, when light shines through the vessel from behind, the entire cup glows with a deep translucent red reminiscent of dark wine. This striking optical transformation is not the result of dyes or pigments, but instead arises from an extraordinarily sophisticated material structure hidden within the glass itself. Modern scientific analysis has revealed that the Lycurgus cup contains microscopic particles of gold and silver suspended throughout the glass matrix. These particles are not merely small. They exist at the nanoscale, measuring roughly 50 to 100 nanometers across. At this size, metals interact with light in unusual ways through a process now known as plasmon resonance, where electrons on the surface of metallic nanoparticles oscillate in response to incoming light waves. The result is a material capable of selectively scattering and transmitting different wavelengths of light, producing the dramatic color-shifting effect seen in the cup. What makes this discovery so astonishing is that this behavior belongs to the field of nanotechnology, a scientific discipline that humans only began to systematically explore in the late 20th century. Yet somehow, nearly 1600 years earlier, Roman artisans created a glass object that embodies these same principles. The most mysterious aspect of this artifact lies in how Roman glassmakers managed to produce such nanoscale metallic particles within molten glass. To achieve the optical properties seen in the Lycurgus cup, gold and silver must be present in extremely small quantities and must be dispersed evenly throughout the material. Modern studies suggest that the mixture contains approximately 70 parts per million of silver and around 40 parts per million of gold. But even slight deviations from this delicate ratio could easily destroy the optical effect entirely, leaving the glass dull or opaque. Achieving this balance would require extraordinary control over the glass-making process. Roman glass production typically involved melting silica sand with soda and lime in large furnaces, reaching temperatures above 1,000 degrees Celsius. During this process, metals could be introduced in powdered or dissolved forms. However, forming nanoparticles of the precise size needed for dichroic behavior requires a complex sequence of chemical reactions, cooling rates, and crystallization conditions. The metals must separate from the molten mixture at just the right stage, and then form clusters small enough to interact with light at the nanoscale. If the clusters grow too large, the optical phenomenon disappears. If they remain too small or disperse unevenly, the effect weakens or vanishes altogether. This delicate balance raises an important question that continues to puzzle historians and materials scientists. Did Roman artisans intentionally engineer this effect, or was it the result of an extraordinarily fortunate accident within the glass-making process? Some researchers believe the phenomenon may have originated through repeated experimentation by skilled craftsmen who carefully observed how small additions of metals altered the appearance of glass. Roman glassmakers were known to produce a wide range of colored glasses using metals such as copper, manganese, and iron. Through centuries of empirical practice, they developed remarkable expertise in controlling color and clarity. It is possible that during these experiments, artisans discovered that very small quantities of precious metals could produce unusual optical effects. Over time, they may have refined a method for reproducing this effect, even if they did not understand the microscopic physics behind it. However, even if such a technique existed, the surviving evidence suggests that it was extremely rare. Only a handful of dichroic Roman glass objects have ever been discovered, and none exhibit the dramatic color contrast of the Lycurgus cup. This rarity suggests that the process was either incredibly difficult to reproduce or was closely guarded within a particular workshop or guild. Equally remarkable is the fact that the Lycurgus cup is not simply a technological curiosity, but also a masterpiece of artistic craftsmanship. The vessel belongs to a rare category of Roman luxury glass known as cage cups or diatrita. In these objects, a decorative outer lattice appears to float around an inner glass vessel, yet both layers were carved from a single piece of glass rather than assembled separately. Achieving this effect required extraordinary patience and precision. Artisans had to grind away large portions of glass while leaving delicate bridges connecting the outer cage to the inner cup. One slip of the tool could shatter the entire object, rendering weeks or months of labor useless. On the Lycurgus cup, this lattice is shaped into an elaborate sculptural narrative depicting the mythological story of King Lycurgus, who opposed the cult of Dionysus and was ultimately punished by the god. In the scene, vines entangle the king as divine figures look on, a symbolic reference to the intoxicating power of wine and divine retribution. The visual drama of the story becomes even more striking when the glass shifts color. When illuminated from behind, the deep red glow enhances the sense that the cup itself is filled with wine, suggesting that the optical effect may have been intentionally designed to enhance the experience of drinking rituals or ceremonial banquets. Despite centuries of study, however, the deeper technological mystery remains unresolved. Modern scientists can replicate dichroic glass using controlled laboratory techniques, but recreating the exact conditions under which Roman craftsmen produced the Lycurgus cup remains challenging. The distribution of nanoparticles inside the glass appears surprisingly uniform, and suggesting that the molten material was mixed and cooled under carefully controlled conditions. Yet the Roman glass industry relied primarily on relatively simple furnaces and manual techniques. Without advanced instruments or theoretical knowledge of atomic structure, how did artisans achieve such precise control over particle formation? Some scholars argue that the phenomenon may have been an unintended byproduct of normal glass-making processes involving metal contamination. Others believe that highly specialized workshops developed experimental recipes that were later lost as the Roman Empire declined and long-distance trade networks collapsed. Another intriguing question concerns why this remarkable technology did not become widespread. If Roman artisans had mastered the ability to create nanostructured glass, one might expect such materials to appear frequently in archaeological finds. Instead, the Lycurgus cup stands almost alone, a technological anomaly emerging briefly in history before disappearing again for more than a millennium. This raises the possibility that the knowledge required to create such glass was never fully understood, even by the artisans themselves. Like many ancient technologies, it may have depended on subtle craft traditions, passed orally from master to apprentice. Once those traditions were broken, the process may have been impossible to reproduce. Today, the Lycurgus cup is preserved in the British Museum, where it continues to fascinate both visitors and scientists. Even after 16 centuries, the vessel still shifts between green and red as light moves around it. To historians, it reflects the remarkable skill of Roman craftsmen. To materials scientists, it reveals an early example of nanotechnology long before the concept was understood. The cup ultimately challenges our assumptions about ancient technology, suggesting that sophisticated material effects could emerge from craftsmanship centuries before modern science explained them. Do you think the nanotechnology effect in the Lycurgus cup was the result of a technique that Roman craftsmen truly understood and intentionally created, or was it simply an accidental discovery during the glass-making process? Share your thoughts in the comments below. The artifact widely known as the Baghdad Battery remains one of the most puzzling and debated discoveries in the history of archaeology and ancient technology. Discovered in 1936 near the village of Kujut Rabu, just outside modern Baghdad in Iraq, the object was first examined by Austrian archaeologist Wilhelm König while working at the National Museum of Iraq. The artifact appeared at first glance to be a simple clay jar, yet its internal components revealed something far more unusual. Dating estimates place it somewhere between approximately 200 BCE and 250 CE, during the era of the Parthian Empire or the early Sassanid period. What has fascinated researchers for decades is that the structure of this seemingly ordinary vessel closely resembles the basic design of a simple electrochemical cell, raising a provocative question that continues to intrigue scientists, historians, and engineers alike. Could people living nearly 2,000 years ago have unknowingly, or perhaps intentionally, created a device capable of producing electricity? At the center of this mystery is the artifact's remarkably battery-like structure, which is the aspect that has drawn the greatest attention from researchers. The object consists of a small clay jar, roughly 13 centimeters tall. Inside the jar sits a cylindrical tube made of copper sheet that has been carefully rolled and soldered along its seam. Suspended within this copper cylinder is an iron rod that runs down the center, held in place by a plug of bitumen or asphalt sealing the top of the container. Importantly, the iron rod does not touch the copper cylinder, leaving a narrow gap between the two metals. This configuration immediately caught the attention of modern scientists because it mirrors the essential components of a primitive galvanic cell. In modern electrochemistry, electricity can be generated when two different metals are immersed in an electrolyte solution and connected through an external circuit. One metal becomes the anode, the other the cathode, and chemical reactions between the metals and the electrolyte create a flow of electrons. The Baghdad artifact seems to replicate this configuration almost perfectly. The iron rod and the copper cylinder represent two different metals with different electrochemical potentials. The clay jar could easily hold a liquid, and if that liquid happened to be acidic, such as vinegar, fermented grape juice, or lemon juice, it could function as an electrolyte. Experiments conducted in the 20th century demonstrated that when a reconstruction of the device is filled with a weak acidic solution, it can produce a small electrical voltage, usually somewhere between half a volt and 1 volt. This is not a large amount of electricity by modern standards, but it is unmistakably measurable. When several such devices are connected in series, the voltage can increase significantly. The fact that the artifact's internal structure unintentionally or intentionally mirrors the fundamental design of a battery has made it one of the most fascinating examples of possible ancient technological ingenuity. This resemblance to a functioning battery has led some researchers to speculate that the device might have been used for electroplating, and a process in which a thin layer of metal is deposited onto the surface of another object using electrical current. Certain ancient artifacts from the Middle East show extremely thin coatings of gold or silver that appear surprisingly uniform. Some scientists have proposed that small electrical currents generated by devices like the Baghdad battery might have been used to apply these coatings. If true, such a process would represent a remarkable technological achievement, since electroplating in the modern scientific sense was not formally developed until the 19th century. The possibility that ancient artisans could have discovered and applied a primitive electrical technique nearly 2 millennia earlier would dramatically change our understanding of early technological experimentation. Yet despite the excitement surrounding this idea, the theory remains highly controversial. One of the main problems is that archaeologists have not discovered clear evidence of wires, connectors, or other components that would normally be required to use such a device in an electrical system. Without conductive wires to carry the current, it becomes difficult to imagine how the electricity generated inside the jar could have been used effectively. Additionally, no ancient texts from the Parthian or Sassanid periods describe the generation or application of electricity. Unlike other technologies, such as metallurgy, glassmaking, or irrigation, there are no written records describing experiments with electrical phenomena. Note, this absence of documentary evidence makes many historians skeptical that the artifact was ever intended to function as a battery. Alternative explanations have therefore been proposed. Some scholars argue that the device might simply have been a container for storing scrolls, sacred objects, or ritual materials. The copper cylinder could have served as a protective casing, while the iron rod might have been part of a structural support or sealing mechanism. In this interpretation, the resemblance to a battery is purely coincidental, a product of modern scientists projecting contemporary technological concepts onto an ancient object whose true function may have been entirely unrelated to electricity. Archaeology often encounters such situations, much where artifacts appear to resemble modern technologies, but were actually used in very different ways within their original cultural contexts. Even so, the physical configuration of the Baghdad battery continues to provoke curiosity. The deliberate arrangement of copper and iron inside a sealed container suggests a design that was not entirely accidental. Copper and iron were widely used metals in ancient metallurgy, yet their specific combination inside a fluid-holding jar invites ongoing speculation. Experimental archaeologists have repeatedly recreated the device to test its capabilities, and in nearly every reconstruction, the result is the same. The system can indeed produce a small electrical charge. Whether this effect was intentionally exploited by ancient craftsmen or merely an accidental byproduct of another function remains one of the central unanswered questions. Another intriguing possibility is that the device represents a form of experimental or isolated technological knowledge that never became widespread. Throughout history, many innovations have appeared briefly and then vanished without leaving a lasting technological tradition. Certain ancient materials, such as Roman self-healing concrete or the legendary Byzantine Greek fire, demonstrate that specialized knowledge can exist within limited communities and later be lost entirely. If the Baghdad battery was part of a small-scale experiment with electrochemical reactions, it is conceivable that the knowledge surrounding it disappeared as political systems changed and skilled artisans vanished. Today, the Baghdad battery stands as a reminder of how incomplete our understanding of ancient technology can be. A small clay jar containing 2 pieces of metal has sparked debates among archaeologists, chemists, historians of science, and engineers for nearly a century. Was it truly an early attempt at generating electricity, centuries before the discoveries of modern electrical science? Was it simply a ritual container whose structure coincidentally resembles a battery? Or does it represent some other technological purpose that researchers have yet to fully understand? Until more definitive evidence emerges, the artifact continues to occupy a fascinating space between archaeology and scientific speculation, challenging our assumptions about what ancient civilizations may or may not have known about the hidden forces of the natural world. Do you think the Baghdad battery was truly an ancient device capable of generating electricity, or just a ritual container that coincidentally resembles a battery? Share your thoughts in the comments below. Among the most astonishing archaeological discoveries in Europe, the Nebra Sky Disc has dramatically reshaped our understanding of prehistoric scientific knowledge. Unearthed in 1999 on the Mittelberg Hill near the town of Nebra in Germany, the artifact dates to around 1600 BCE during the European Bronze Age. At first glance, the object appears deceptively simple: a bronze disc, roughly 30 centimeters in diameter, decorated with thin gold inlays representing celestial bodies. Yet closer examination reveals something extraordinary. Rather than merely serving as decoration or symbolic art, the arrangement of the gold elements appears to encode a sophisticated understanding of the sky. For archaeologists and historians of science, the disc has become one of the earliest known attempts by humans to visually represent astronomical knowledge in a portable form, suggesting that Bronze Age societies in Central Europe may have possessed a surprisingly advanced awareness of celestial cycles. The surface of the disc contains 32 small gold circles interpreted as stars, along with a large round golden plate believed to represent either the sun or a full moon. Beside it appears a delicate crescent shape widely interpreted as a waxing moon. Among the stars a cluster of 7 is arranged in a pattern closely resembling the Pleiades, one of the most recognizable star groups in the night sky. This detail alone is remarkable because the Pleiades played a crucial role in many ancient agricultural calendars. Across multiple early civilizations, the appearance and disappearance of this star cluster marked seasonal transitions important for planting and harvesting. The Nebra Sky Disc therefore suggests that the people who created it were not simply observing the sky casually, but were systematically tracking celestial patterns that influence their daily lives. However, what truly distinguishes the Nebra Sky Disc from other prehistoric artifacts is a set of curved gold arcs added to the sides of the disc during a later stage of modification. These arcs have become the focus of intense scientific debate because their angular span measures approximately 82 degrees. This number is not random. At the latitude of central Germany, and the difference between the positions of the rising sun at the summer solstice and the winter solstice also measures roughly 82 degrees along the horizon. This remarkable correspondence suggests that the arcs may represent a system for identifying the extreme rising and setting points of the sun throughout the year. If this interpretation is correct, the Nebra Sky Disc may have functioned as a form of portable astronomical instrument capable of helping observers determine the turning points of the solar cycle. Understanding the significance of this feature requires appreciating the complexity of solar observation. Determining the precise locations where the sun rises and sets on the horizon at different times of the year is not something that can be accomplished through casual observation, since it requires careful tracking of the sun's movement across multiple seasons and often across multiple years. Over time, an observer would notice that the sunrise gradually shifts along the horizon day by day until it reaches a maximum point at the summer solstice. After that moment, the direction reverses, and the sunrise begins moving back toward the south until it reaches its opposite extreme at the winter solstice. Identifying these limits requires long-term astronomical awareness and careful spatial measurement. The fact that the arcs on the Nebra Sky Disc correspond so closely to this angular range implies that the creators of the disc may have been observing solar movement for generations before encoding that knowledge into a physical object. If the disc was indeed used as a tool to identify solstices, it would have been an extraordinarily valuable device for Bronze Age societies dependent on seasonal cycles. The solstices represent key turning points in the solar year, marking the longest and shortest days. Agricultural planning, ritual calendars, and social ceremonies were often aligned with these astronomical moments. A portable device, capable of illustrating these solar boundaries, could therefore function as both a teaching instrument and a ceremonial object, linking cosmological knowledge with cultural authority. Some researchers have proposed that the disc might have been aligned with the local landscape when used. When held or positioned correctly, the arcs could theoretically match the positions of sunrise or sunset relative to distant horizon features, effectively transforming the disc into a symbolic horizon map. The technological implications of this interpretation are profound. Bronze Age Europe is not typically associated with advanced observational astronomy. Prior to the discovery of the Nebra Sky Disc, complex astronomical knowledge in ancient times was usually attributed to civilizations such as Babylon, Egypt, or later classical Greece. The presence of such knowledge in Central Europe, more than 3,500 years ago, challenges earlier assumptions about the intellectual capabilities of prehistoric European societies. The disc suggests that systematic sky observation may have been more widespread than previously believed, and that knowledge of celestial cycles could have circulated across long-distance cultural networks. But further adding to the mystery, is the sophisticated craftsmanship involved in creating the disc itself. The bronze base was carefully forged and then decorated with thin sheets of gold that were cut into precise shapes and hammered into the surface. Scientific analyses have revealed that the copper used in the bronze likely originated in the Alpine region, while the gold may have come from areas in the Carpathian Mountains. The tin necessary for producing bronze could have been sourced from regions as distant as Cornwall in Britain. These findings indicate that the people responsible for the disc were connected to extensive trade networks spanning large parts of Europe. Such networks may also have facilitated the exchange of astronomical ideas and observational techniques. The disc did not remain static over time, and evidence shows that it underwent several phases of modification. The side arcs representing the solar horizon range were added after the original star pattern had already been created, suggesting that the disc's astronomical meaning evolved. Later still, another golden arc was added to the lower edge of the disc. Many scholars interpret this final element as a representation of a solar bark, a mythical boat carrying the sun across the heavens, a motif that appears in several ancient cultures. The addition of this symbol may indicate that the disc had begun to take on religious or mythological significance beyond its original astronomical function. Despite decades of research, many aspects of the Nebra Sky Disc remain unresolved. One of the most puzzling questions concerns how the original observers were able to measure the solar horizon range so accurately. Achieving an 82-degree measurement requires either careful horizon markers or long-term observational records. Yet archaeologists have not discovered definitive instruments from the same culture that could have been used for such measurements. It remains possible that wooden structures, stone markers, or natural landscape features once served as observation points but have since disappeared. Alternatively, the knowledge may have been preserved through oral traditions and accumulated observation across generations. Another unresolved issue concerns the role of the disc within Bronze Age society. It was discovered alongside weapons and valuable objects, suggesting that it belonged to an elite individual. Some researchers propose that the disc functioned as a prestige item, symbolizing authority derived from celestial knowledge. In many ancient cultures, individuals who understood the movements of the heavens often held powerful positions within religious or political hierarchies. The Nebra Sky Disc may therefore represent not only astronomical knowledge, but also the social power associated with controlling that knowledge. Today, this artifact continues to challenge traditional views of ancient science. It shows that prehistoric societies were capable of observing the sky with patience and accuracy, and of attempting to record that knowledge in lasting, symbolic forms. The golden arcs, marking the sun's yearly movement, may be the most significant feature, and suggesting an effort to represent astronomical patterns on a physical object. Whether used as an observational tool, a ritual object, or a means of transmitting knowledge, the Nebra Sky Disc remains one of the earliest examples of humans trying to transform the laws of the sky into a tangible form of technology. More than 3,000 years after it was created, the disc still forces us to reconsider how ancient people understood the heavens and their place within the universe. Do you think the Nebra Sky Disc was merely a ritual symbol with mythological meaning, or could it actually have been an ancient astronomical tool used to track the movement of the sun? Share your thoughts in the comments below. The Nimrud crystal lens, sometimes referred to as the layered lens, is one of the most intriguing small artifacts ever discovered from the ancient world. Unearthed in the 19th century during excavations at the ancient Assyrian city of Nimrud by the British archaeologist Austen Henry Layard, this modest piece of rock crystal has sparked more than a century of debate among historians, archaeologists, and scientists. Today, the object is preserved in the collections of the British Museum, where it continues to attract attention, not because of its size, but because of the profound technological questions it raises. The lens dates to roughly the 8th century BCE, during the height of the Neo-Assyrian Empire, a civilization already famous for its monumental architecture, intricate relief carvings, and advanced administrative systems. Yet the existence of this small, polished crystal suggests that the Assyrians may also have possessed a level of practical knowledge about materials and optics that historians are still trying to understand. At first glance, the Nimrud crystal lens appears deceptively simple. It is a roughly oval piece of transparent rock crystal measuring only a few centimeters across, slightly convex on one side and somewhat flatter on the other. However, when examined closely, the object reveals a remarkable property. It is capable of magnifying images. Modern tests have shown that it can enlarge objects by roughly 2 to 3 times, enough to noticeably sharpen fine details. This alone would make the artifact fascinating, because if it was intentionally shaped to function as a magnifying lens, it would represent one of the earliest known optical devices in human history. Most traditional histories of science place the development of practical lenses much later, particularly in the Greek, Roman, and medieval European worlds. The possibility that such an object existed in Assyria nearly 3,000 years ago therefore forces scholars to reconsider how early knowledge of optical principles may have appeared. Yet the true mystery of the Nimrud crystal lens does not lie only in its ability to magnify. The deeper puzzle lies in the precision with which the crystal itself was shaped and polished. Rock crystal, a form of natural quartz, is not an easy material to work with. On the Mohs scale of mineral hardness, it ranks around 7, significantly harder than many stones typically used in ancient carving. Cutting and shaping such a material requires abrasives, patience, and a controlled technique capable of gradually grinding down the surface without shattering the crystal. Even in later historical periods, artisans often relied on specialized tools and carefully selected grinding compounds to achieve smooth optical surfaces. For this reason, the existence of a curved, polished crystal object from the Assyrian period immediately raises technical questions about how it was produced. When scientists examine the surface of the Nimrud lens, they observe that it possesses a subtle curvature rather than a flat plane. This curvature is what allows it to function as a magnifying lens. Creating such a surface is not simply a matter of randomly polishing stone. It requires removing material in a controlled manner so that the crystal gradually forms a consistent convex shape. In modern optics, lenses are manufactured by grinding and polishing glass, using extremely precise mechanical processes designed to maintain uniform curvature across the entire surface. Of course, the Nimrud artifact is not perfectly symmetrical by modern standards, and small irregularities exist within the crystal itself. Nevertheless, the overall shape indicates deliberate shaping rather than accidental erosion or natural fracture. This leads to a fascinating technological question. How did Assyrian craftsmen achieve this level of shaping accuracy using the tools available to them nearly 3 millennia ago? Our archaeological evidence from Mesopotamia shows that artisans were highly skilled in working with hard materials such as gemstones, ivory, and metal. They possessed copper and bronze tools, abrasives made from harder minerals, and polishing techniques capable of producing extremely fine, decorative surfaces. Yet shaping transparent quartz into a curved optical surface would still have been a delicate and time-consuming process. Some researchers believe the lens was gradually ground using fine sand or powdered minerals combined with water, slowly wearing down the surface while repeatedly polishing it to maintain clarity. Others suggest that the curvature might have been achieved through multiple stages of grinding, each progressively refining the shape. And what makes this especially intriguing is that the artisans would have needed some way to judge whether the surface curvature was correct. In modern lens making, craftsmen test optical surfaces by measuring their geometry or by observing how light passes through them. If the Nimrud lens was indeed intended to magnify objects, then the craftsman who shaped it may have used simple visual testing, holding the crystal over small objects and adjusting the curvature until the magnification improved. Such a process would not require a theoretical understanding of optics in the mathematical sense, but it would imply an empirical knowledge gained through experimentation. In other words, ancient artisans may have discovered that certain shapes of polished crystal could enlarge images, and through repeated practice, they learned how to reproduce that effect. Another layer of complexity lies in the internal imperfections of the crystal itself. Rock crystal often contains natural inclusions, fractures, and distortions. The Nimrud lens displays several of these features, which cause slight distortions when viewed through it. If the artifact was intended as a precision optical device, these imperfections might seem problematic. However, they also highlight the remarkable patience required to shape the object without causing it to crack. Working quartz is risky, because stress during grinding can easily split the crystal along natural planes. The fact that the lens survived the shaping process suggests that the artisan possessed considerable skill and experience with the material. The intended purpose of the lens remains another subject of debate. One widely accepted hypothesis proposes that it served as a magnifying aid for craftsmen, allowing jewelers, engravers, or scribes to see extremely fine details while working. Assyrian artifacts often display extraordinarily intricate patterns carved into small surfaces, including delicate reliefs and miniature inscriptions. A magnifying lens would have been an invaluable tool for artisans attempting to produce such precision. Another theory suggests that the crystal might have been used to concentrate sunlight to start fires, functioning in a manner similar to a modern burning glass. There are also more speculative ideas proposing that it could have played a role in early observational astronomy, though no clear evidence links the Assyrians to telescopic devices. Despite decades of study, scholars still cannot fully explain the technological context of the Nimrud crystal lens. Was it an isolated experiment created by a particularly innovative artisan, or was it part of a broader but poorly documented tradition of optical craftsmanship in the ancient Near East? Other ancient objects made from polished crystal have been discovered in places such as Pompeii and on the island of Crete, suggesting that the idea of shaping transparent materials may have appeared in multiple cultures independently. Yet none of these artifacts conclusively demonstrate a widespread technology comparable to later optical science. In the end, yet the Nimrud crystal lens remains a small yet powerful reminder that ancient technology may have been far more sophisticated than we often assume. This tiny piece of polished quartz suggests a surprising level of skill in shaping and polishing hard crystal, hinting at careful experimentation with light and materials nearly 3,000 years ago. Whether it was a practical tool, a scientific curiosity, or simply a decorative object, the artifact still raises an enduring question. How much technical knowledge did ancient civilizations truly possess, and how much of it has been lost to time? What do you think the Nimrud crystal lens was really used for? A magnifying tool, an ancient optical experiment, or something we still don't fully understand? Share your thoughts in the comments below. Among the many remarkable technologies developed by ancient civilizations, few are as intriguing, mysterious, and chemically sophisticated as the production of Tyrian purple, one of the most prized and symbolically powerful pigments in human history. This legendary dye originated in the maritime civilization of Phoenicia, particularly in the prosperous coastal city of Tyre, from which the dye ultimately derived its name. For centuries, Tyrian purple represented far more than a simple color. It was a visual declaration of authority, wealth, and divine legitimacy. Kings, emperors, and high-ranking elites throughout the Mediterranean world coveted fabrics dyed in this rare pigment, and in some periods, strict laws limited its use exclusively to imperial families. Yet behind its political symbolism lay a technological process of extraordinary complexity, one that relied on biological materials, photochemical reactions, and carefully controlled conditions that ancient craftsmen mastered long before the formal development of chemistry as a scientific discipline. The dye was produced from marine snails belonging to the genus Murex, particularly the species Balinus brandaris and Hexaplex trunculus, which inhabit the rocky shores of the Mediterranean Sea. These snails contain a tiny gland that secretes a colorless or pale liquid used in their natural defense system. Remarkably, the vivid purple pigment that made Tyrian dye so famous does not exist in the snail in its final form. Instead, the color emerges through a complex sequence of chemical transformations triggered by exposure to sunlight and oxygen. Ancient dye makers first extracted the gland from the snail and crushed it to release its secretion. This substance initially appeared milky white or slightly yellowish. When exposed to air and sunlight, however, it began to change color gradually, passing through shades of green and blue before finally stabilizing into the deep, luxurious purple that became synonymous with royal power. This transformation occurs through a photochemical oxidation process, meaning that ultraviolet light plays a critical role in altering the molecular structure of the pigment precursor. The fact that ancient artisans discovered and mastered this delicate chemical reaction without modern instruments suggests a remarkable tradition of empirical experimentation and observation. Archaeological discoveries reveal that the production of Tyrian purple was not a small craft activity, but rather a surprisingly large-scale industry. Excavations in Phoenician centers such as Sidon, Tyre, and later Phoenician colonies like Carthage have uncovered enormous mounds of discarded murex shells, sometimes forming archaeological layers several meters thick. These deposits provide dramatic evidence of the immense quantities of marine snails required for dye production. Estimates suggest that thousands, sometimes even 10,000 snails, were needed to produce just a few grams of dye sufficient to color a small piece of cloth. The presence of such vast shell accumulations indicates a highly organized system of harvesting, processing, and distribution. Workers likely collected the snails along rocky coastlines, transported them to specialized workshops, and processed them in large vats, where the glands were crushed and fermented. The smell of these workshops must have been extraordinarily unpleasant. Ancient writers even described the production of purple dye as a foul-smelling process. Yet despite these difficulties, the dye remained one of the most profitable industries in the Mediterranean world, generating immense wealth for Phoenician merchants who traded purple textiles across vast maritime networks. However, the most fascinating and unresolved aspect of Tyrian purple technology lies in the chemical secrets behind its production. Yet modern chemical analysis has revealed that the key pigment responsible for the famous purple color is a compound known as 6,6-dibromoindigo, a brominated variant of the indigo molecule. This compound forms when certain precursors present in the snail's gland undergo oxidation and photochemical transformation. While scientists now understand the basic molecular structure of the dye, recreating the exact ancient process has proven surprisingly difficult. Laboratory experiments can produce similar compounds, but the shades achieved often differ subtly from those found in ancient textiles preserved in archaeological contexts. Some modern reproductions appear more bluish, while others lack the remarkable depth and richness characteristic of authentic Tyrian purple. This discrepancy suggests that ancient craftsmen possessed a level of practical knowledge about the dyeing process that has not been fully recovered. One of the major challenges in reconstructing the ancient technique lies in the number of variables involved in the dyeing process: temperature, fermentation duration, exposure to sunlight, oxygen concentration, and even the specific species of snail used all influence the final color. Slight variations in any of these factors can dramatically alter the resulting pigment. Ancient dye makers likely monitored these variables carefully, adjusting their methods based on visual cues and accumulated experience. Unlike modern industrial chemistry, which relies on standardized formulas and precise measurements, ancient artisans probably depended on sensory observation, watching subtle shifts in color, detecting changes in smell, and judging the texture of the fermenting mixture. Such experiential knowledge would have been transmitted through apprenticeship rather than written documentation, making it extremely vulnerable to loss if the tradition were disrupted. Another unresolved mystery concerns the possibility that ancient craftsmen used additional materials or environmental conditions that modern researchers have not yet identified. Some scholars have proposed that mineral additives present in the dyeing vats may have influenced the reaction chemistry, stabilizing certain pigment forms or altering the final hue. Others suggest that the shape and material of the fermentation vessels themselves could have affected temperature control or oxygen exposure. Even the timing of sunlight exposure may have been critical, as the photochemical reactions involved depend strongly on ultraviolet radiation. Without detailed written records from Phoenician dye workshops, these subtle aspects of the process remain largely speculative. The remarkable durability of Tyrian purple further deepens the mystery. Unlike many natural dyes derived from plants, which fade rapidly when exposed to sunlight, Tyrian purple is extraordinarily stable. Fabrics dyed with this pigment can retain their color for thousands of years, and in some cases, the purple hue appears even more vivid with age. This resilience arises from the molecular structure of 6,6-dibromoindigo, which binds strongly to textile fibers and resists degradation from ultraviolet light. Yet even here, modern reconstructions sometimes fail to match the longevity and brilliance of ancient samples, suggesting that ancient production methods may have generated subtle molecular variations not fully replicated under laboratory conditions. Because of its rarity and extraordinary production cost, Tyrian purple quickly became associated with political authority. During the height of the Roman Empire, laws strictly regulated who could wear garments dyed in this prestigious color. Only emperors and high-ranking officials were permitted to display the deepest shades of purple, while lesser elites were restricted to diluted variations. Later, in the Byzantine Empire, the symbolism of the dye became even more powerful, and children born to ruling emperors were described as born in the purple, a phrase that reflected the exclusive association between the dye and imperial legitimacy. Possessing Tyrian purple was not merely a matter of fashion, it was a statement of sovereignty and divine authority. Over time, however, the intricate knowledge required to produce the dye gradually disappeared. Political instability, economic changes, and the transformation of trade networks during the late medieval period contributed to the decline of Mediterranean dye industries. As the workshops closed and the specialized craftsmen vanished, the practical knowledge accumulated over centuries faded as well. By the early modern period, the authentic production of Tyrian purple had effectively ceased, leaving behind only archaeological remains, scattered historical references, and tantalizing chemical clues embedded in ancient textiles. Today, Tyrian purple dye technology remains both a testament to the ingenuity of ancient civilizations and a reminder of how fragile technological knowledge can be. Long before the science of chemistry existed, Phoenician artisans had already mastered a complex process involving marine biology, fermentation, oxidation, and sunlight-driven reactions. Despite modern scientific advances, researchers still struggle to reproduce the exact qualities of this ancient dye. As a result, Tyrian purple endures not only as a symbol of royal power, but also as one of the most intriguing technological mysteries of the ancient world. Do you think the Phoenicians truly possessed a special chemical secret that allowed them to create Tyrian purple in a way modern science still cannot fully reproduce? Or was it simply the result of centuries of experimentation and inherited craftsmanship? Share your thoughts in the comments below. The techniques used to transport the enormous stone blocks that built the pyramids of the Giza Pyramid Complex remain one of the most fascinating engineering mysteries of the ancient world. Among these monuments, the Great Pyramid of Giza, constructed during the reign of Khufu around 2600 BCE, stands as the most extraordinary example of large-scale stone engineering in human history. The pyramid contains roughly 2.3 million limestone and granite blocks, with most weighing between 2 and 15 tons, while some of the granite beams used in the king's chamber weigh more than 60 tons. The existence of such massive stones, stacked with remarkable precision, raises a fundamental question that continues to challenge archaeologists, engineers, and historians alike. How did a civilization, equipped with relatively simple tools, manage to transport and position millions of tons of stone across desert terrain and lift them to great heights with such astonishing efficiency? The logistical challenge alone is staggering. If the Great Pyramid was completed within approximately 20 years, as most scholars estimate, builders would have needed to place an average of several hundred blocks every single day. This implies a continuous, highly organized system capable of moving stone blocks from quarries to the construction site with incredible regularity. Limestone used for the pyramid's core was quarried locally on the Giza Plateau, but higher quality casing stones were transported from quarries across the Nile. The massive granite blocks used in interior chambers were brought from Aswan quarries, located hundreds of kilometers to the south. These granite blocks, some weighing up to 70 tons, were most likely transported along the Nile on large wooden barges during the annual flood season, when water levels were high enough to support heavy cargo. Yet even if river transport solved part of the puzzle, a more difficult question remains unresolved. How were these enormous stones moved from the riverbank across the desert plateau and lifted gradually into the rising structure of the pyramid? Evidence suggests that workers used wooden sledges rather than wheeled vehicles, since the wheel was not commonly used for heavy transport in ancient Egypt. Reliefs and paintings, such as one found in the tomb of Jehutihotep, use show teams of workers pulling colossal statues on large wooden sledges, while another worker pours water onto the sand in front of the sled. Modern experiments have demonstrated that wetting sand can significantly reduce friction, allowing heavy loads to slide more easily across the desert surface. This simple but ingenious technique suggests that Egyptian builders possessed practical knowledge of mechanical principles long before the development of formal scientific theory. Even so, dragging a multi-ton block across kilometers of desert would still have required coordinated teams of laborers and careful planning, highlighting the extraordinary organizational abilities of the pyramid builders. However, the greatest and most enduring mystery surrounding pyramid construction lies not in moving stones across flat ground, but in raising them upward as the pyramid itself grew taller. The most widely accepted explanation involves the use of massive construction ramps. Yet the exact design of these ramps remains one of the most debated problems in Egyptology. According to the simplest theory, builders created a large, straight ramp extending from the ground up the side of the pyramid. Workers could then drag stone blocks up the ramp using sledges until they reached the desired level. While this explanation appears straightforward, it quickly becomes problematic when examined in terms of scale. To maintain a slope gentle enough for workers to pull heavy stones, the ramp would have needed to extend for more than a kilometer in length. The amount of material required to build such a ramp, composed of mud brick, limestone debris, and sand, might have exceeded the total volume of the pyramid itself. Furthermore, almost no physical traces of such an enormous structure have been discovered near the pyramid complex, raising doubts about whether a single straight ramp could ever have existed. Because of these challenges, many researchers have proposed alternative ramp systems, each attempting to solve the problem of lifting stones efficiently without requiring impossible quantities of construction material. One popular theory suggests a spiral ramp that wrapped around the outer surface of the pyramid as it rose higher. In this model, workers could drag blocks along a gradually ascending pathway that circled the structure. However, this idea introduces another difficulty. A spiral ramp would have obscured the edges of the pyramid during construction, making it extremely difficult for builders to maintain the monument's precise geometric alignment. The Great Pyramid is famous for its remarkable accuracy, with its sides aligned almost perfectly with the cardinal directions and its base forming an almost flawless square. Maintaining such precision while a massive ramp covered the exterior would have been extremely challenging. Another intriguing hypothesis proposes that the ramp system may have been partially internal. According to this theory, builders constructed a network of ramps and corridors within the outer layers of the pyramid itself. Stones could have been dragged through these internal passageways, gradually spiraling upward as each layer was completed. And some modern architectural analyses of the pyramid's structure suggest that hidden voids or corridors may exist within the walls, leading some researchers to speculate that these spaces could represent remnants of such an internal ramp system. While this idea elegantly explains how stones might have been lifted without enormous external ramps, definitive archaeological evidence remains limited, leaving the theory controversial. Other scholars have proposed hybrid solutions involving multiple ramps that were built, dismantled, and rebuilt as construction progressed. In this scenario, a large ramp might have been used during the early stages when the pyramid was relatively low, while smaller ramps or levering systems could have been employed as the structure reached greater heights. Ancient builders may also have used wooden levers and counterweights or temporary platforms to maneuver the stones into precise positions. Yet even with these ideas, many questions remain unanswered. The absence of detailed construction records from ancient Egypt means that modern researchers must rely heavily on experimental archaeology and engineering simulations to reconstruct the building process. What makes the ramp mystery especially compelling is that no single theory fully accounts for every aspect of the pyramid's construction. Each proposed solution explains some elements while leaving others unresolved. Straight ramps demand impractical amounts of material, spiral ramps complicate alignment, and internal ramps remain archaeologically unconfirmed. As a result, the exact system used by ancient Egyptian builders may have been far more complex than any single model suggests. And it is possible that multiple techniques were combined in creative ways, reflecting a level of engineering ingenuity that still surprises modern researchers. In the end, the question of how the stones of the Great Pyramid were transported and lifted remains partly unanswered. Archaeological discoveries, such as the Diary of Mera, provide glimpses into the logistics of moving limestone along the Nile, revealing organized teams of workers and carefully planned supply routes. Yet these records stop short of describing the actual methods used to raise stones into the towering structure we see today. The ramp system, whatever its true design, remains the central puzzle in the story of pyramid construction. More than 4,000 years after the Great Pyramid was completed, it still stands not only as a monumental tomb, but also as a silent testament to the engineering abilities of a civilization whose practical knowledge of construction and logistics continues to challenge our understanding of ancient technology. In your opinion, what type of ramp system did the ancient Egyptians actually use to lift millions of stone blocks to the top of the pyramid? A straight ramp, a spiral ramp, or a completely different system that we have not yet discovered? Share your thoughts or theories in the comments section below. Across the humid lowlands of the Gulf Coast of Mexico, long before the rise of the Maya or the Aztec, the civilization known today as the Olmec civilization created a range of artifacts that continue to puzzle archaeologists and materials scientists. Among the most intriguing of these objects are the Olmec polished obsidian mirrors, mysterious circular or oval discs carved from volcanic glass and polished to an extraordinary reflective finish. At first glance, these mirrors appear deceptively simple. They are small, dark, and often undecorated, yet closer examination reveals a level of technical sophistication that seems astonishing for a society that flourished more than 3,000 years ago. Obsidian is not an easy material to work with. It forms when molten lava cools rapidly, miscreating a natural glass with extremely sharp fracture edges and a brittle internal structure. Because of this, obsidian was commonly used throughout ancient Mesoamerica for cutting tools, blades, and spear points, where its razor-sharp edges were advantageous. However, shaping large, flat, reflective surfaces from this material is a completely different challenge. The slightest mistake in grinding or polishing can cause cracks, chips, or irregular surfaces that ruin the reflective quality of the stone. Despite these difficulties, Olmec artisans managed to produce mirrors with surfaces so smooth and uniform that they could reflect light and images with remarkable clarity. Archaeological discoveries suggest that these mirrors were not ordinary objects used for daily life. Many have been found in elite burials or ceremonial contexts at major Olmec centers, such as La Venta and San Lorenzo Tenochtitlan. Their placement in ritual settings indicates that they likely carried symbolic or spiritual significance. Later, Mesoamerican traditions provide intriguing clues. In the cosmology of the Aztec civilization, the powerful deity Tezcatlipoca was closely associated with obsidian mirrors, which were believed to reveal visions, divine messages, or glimpses into hidden realms. While these beliefs developed many centuries after the Olmec period, some scholars believe the symbolic importance of obsidian mirrors may have originated with the Olmec themselves. The reflective surface of obsidian has a deep, almost liquid darkness that can appear mysterious and hypnotic when illuminated by firelight or sunlight. Seen in ritual settings, such mirrors may have been used for divination, meditation, or ceremonial performances that emphasized the connection between the physical world and the supernatural. Beyond their symbolic significance, however, the mirrors present a much deeper technological mystery. The most striking feature of Olmec obsidian mirrors is the precision of their polished surfaces. Many specimens display extremely smooth, evenly curved surfaces that suggest deliberate control over the geometry of the mirror. Some are slightly concave, meaning they may have functioned as primitive optical devices capable of concentrating light. Experiments conducted by modern researchers have demonstrated that certain obsidian mirrors can focus sunlight strongly enough to ignite dry plant material under favorable conditions. Whether the Olmec intentionally designed these mirrors to achieve such optical effects remains uncertain, but the possibility highlights the remarkable craftsmanship involved in their creation. Achieving such curvature and smoothness would have required careful shaping, gradual grinding, and an extended polishing process using abrasive materials. Yet the greatest mystery surrounding these artifacts lies in how the Olmec achieved their extraordinary level of polish in the first place. Obsidian is relatively hard and extremely brittle, which makes polishing it to a mirror finish both technically demanding and time-consuming. Modern experimental archaeology has attempted to reproduce the techniques that might have been used by ancient craftsmen. Researchers have experimented with grinding obsidian surfaces using sandstone, fine sand, and water, followed by polishing with increasingly finer abrasives. While these methods can eventually produce reflective surfaces, the results rarely match the quality of many Olmec mirrors. Even after hundreds of hours of labor, modern replicas often display microscopic irregularities that scatter light and reduce the clarity of reflection. In contrast, several ancient mirrors demonstrate surfaces so smooth that they rival polished stone mirrors from much later historical periods. This discrepancy has led researchers to suspect that Olmec artisans possessed specialized polishing techniques or materials that have not yet been fully identified. One theory proposes that extremely fine mineral powders may have been used during the final stages of polishing. Substances such as powdered hematite, silica, or other naturally occurring abrasives could have gradually refined the surface to a near-perfect finish. However, direct archaeological evidence for these materials is scarce. Another possibility is that artisans used organic compounds mixed with mineral abrasives to create polishing pastes capable of smoothing microscopic imperfections. Because organic materials rarely survive for thousands of years in tropical environments, any such compounds would likely have disappeared from the archaeological record. As a result, the precise technological sequence used to produce these mirrors remains largely speculative. What is clear, however, is that the process must have required enormous patience, skill, and experience. Creating a single mirror may have demanded many days or even weeks of continuous grinding and polishing. The mystery deepens when researchers consider the broader technological context of the Olmec civilization. The Olmec did not possess iron tools or advanced metalworking technologies that could assist in shaping hard materials. Their tools were primarily made from stone, bone, or wood. Yet despite these limitations, they produced mirrors with surfaces that appear almost mathematically regular. This suggests that Olmec artisans developed sophisticated craft traditions passed down through generations. Skilled specialists may have devoted their entire careers to mastering the delicate art of obsidian polishing. The knowledge required to achieve such precision may have been closely guarded within elite workshops, making it difficult for modern scholars to reconstruct the process. Another layer of intrigue concerns the origin of the obsidian itself. Geological analysis has shown that the obsidian used in some Olmec mirrors originated from volcanic sources located hundreds of kilometers away from the Olmec heartland. This indicates the existence of long-distance trade networks that transported raw materials across Mesoamerica. The selection of specific obsidian sources may not have been random. Certain volcanic deposits produce obsidian with particularly uniform internal structures and fewer microscopic impurities, making them more suitable for polishing into reflective surfaces. If Olmec craftsmen deliberately sought out these high-quality materials, it would demonstrate an advanced understanding of stone properties and resource selection. Even after decades of research, the polished obsidian mirrors of the Olmec civilization remain among the most mysterious artifacts of ancient Mesoamerica. While archaeologists continue to study their ritual and cultural significance, the greatest puzzle lies in the craftsmanship itself. The precise techniques used to polish obsidian to such extraordinary smoothness have not yet been fully recreated by modern researchers. This unresolved mystery suggests that ancient craft knowledge may have been far more advanced than we once believed, leaving behind a technological skill that is still only partially understood today. In your opinion, how were the Olmec able to polish obsidian to such an extraordinary level of perfection, using extremely simple tools more than 3,000 years ago? Share your thoughts in the comments below. The vast desert plateau of southern Peru hides one of the most perplexing engineering achievements of the ancient world: the Nazca geoglyphs, commonly known as the Nazca lines. Created by the Nazca civilization roughly between 500 BCE and 500 CE, these enormous drawings stretch across the arid plains of the Nazca Desert, covering an area of hundreds of square kilometers. At first glance, the technique used to create them appears deceptively simple: removing the dark, oxidized stones from the desert surface to expose the lighter soil beneath. Yet behind this simplicity lies a technical and surveying mystery that continues to puzzle archaeologists, engineers, and historians alike. What makes the Nazca lines extraordinary is not merely their scale, but the remarkable geometric precision achieved by a culture that possessed no known advanced surveying instruments, no aerial perspective, and no written technical manuals. The most striking and mysterious aspect of the Nazca surveying technique is the enormous geometric accuracy achieved across distances that can extend hundreds of meters or even several kilometers. Many of the geoglyphs, including the famous hummingbird, spider, monkey, and condor, measure between 100 and 300 meters in length, while some of the straight lines stretch across the desert for several kilometers without significant deviation. When viewed from above, whether from a nearby hill, a drone, or an airplane, the shapes appear astonishingly balanced and proportionally correct, and the symmetry of many figures suggests careful planning and mathematical awareness. Yet the paradox remains clear. These images were designed on the ground, by people who could not see the finished figure from the vantage point necessary to fully appreciate its form. From the surface of the desert, most of the shapes are nearly impossible to recognize. The challenge of maintaining proportions across such vast scales raises a fundamental question that still remains unresolved. how did the Nazca people maintain precise geometric control over drawings that were far larger than anything they could visually grasp from the ground? One hypothesis suggests that the Nazca used a system of wooden stakes and cords to establish reference points across the desert surface. Archaeologists have indeed discovered several ancient wooden stakes at Nazca, some of which were carbon dated to the period when the geoglyphs were created. These stakes could have served as anchors for stretched ropes, allowing builders to create straight lines between 2 points. In theory, this method could produce accurate straight lines over considerable distances. Experimental archaeologists have demonstrated that small teams using only ropes and stakes can replicate simple geoglyph shapes. However, when these experiments attempt to reproduce the complexity and scale of the original Nazca figures, significant difficulties arise. Maintaining proportional accuracy across hundreds of meters requires not only straight reference lines, but also a systematic way of transferring scaled designs onto the ground. Without an aerial viewpoint, even minor deviations in angle or length could distort the entire figure. The fact that many Nazca figures remain visually coherent when viewed from high altitude suggests that the builders possessed an unexpectedly sophisticated understanding of large-scale geometry. Equally remarkable are the hundreds of straight lines that crisscross the desert landscape. Some extend for several kilometers, maintaining direction with astonishing consistency even when they traverse uneven terrain or gentle slopes. Modern surveying instruments such as theodolites and laser alignment tools make such precision routine today, but the Nazca people possess none of these technologies. Scholars have proposed that distant landmarks, such as mountain peaks on the horizon, may have served as visual alignment markers. By fixing their sightlines on prominent geographic features, Nazca surveyors might have maintained straight orientations over long distances. Another possibility involves astronomical alignments, where the position of the sun, stars, or seasonal solstices could have provided directional guidance. Some researchers have suggested that certain lines correspond to solar or celestial events, although this theory remains controversial and not universally supported by the archaeological evidence. Beyond individual lines and figures, the entire Nazca landscape appears to exhibit a degree of spatial planning that implies deliberate organization. The geoglyphs do not appear randomly scattered. Instead, they occupy particular zones within the desert, often avoiding overlap, even though they were created over centuries. This suggests that the Nazca people may have maintained some form of large-scale planning system. If multiple generations contributed to the creation of the geoglyphs, they must have shared an understanding of where new designs could be placed without disrupting existing ones. Yet no physical maps, diagrams, or planning tools have ever been discovered. The absence of such artifacts raises another puzzle. How was knowledge of the geoglyph layout preserved and transmitted across generations? Another intriguing aspect of the Nazca surveying process lies in the creation of curves and organic shapes. Many of the famous animal figures display graceful arcs and flowing outlines, yet these curves are actually constructed from a series of short, straight segments. This suggests that the Nazca builders may have plotted multiple reference points before connecting them with linear segments, producing the illusion of a smooth curve when viewed from a distance. Such a method would indicate a form of geometric plotting, similar to techniques used in early architectural drafting. However, if such systems existed, the tools or measuring devices used to establish these points have not survived in the archaeological record. Perhaps the most enduring mystery is how the Nazca people verified their work. Creating a design that spans hundreds of meters requires periodic inspection of the entire figure. Yet without elevated observation platforms, it would have been nearly impossible to confirm whether a figure was proportionally correct until it was complete. Some researchers propose that surrounding hills may have served as observation points. Indeed, certain geoglyphs are partially visible from nearby slopes. However, many of the most iconic figures are only fully recognizable from much greater heights, suggesting that even these natural viewpoints would not have revealed the complete design. Despite these unanswered questions, the durability of the Nazca lines demonstrates another subtle form of environmental understanding. The Nazca Desert is one of the driest places on Earth, experiencing extremely little rainfall and minimal wind erosion. By removing the darker surface stones and exposing the lighter soil beneath, the Nazca builders created high-contrast images that have survived for more than 15 centuries. In many cases, the displaced stones were carefully arranged along the edges of the lines, forming low ridges that help protect the shapes from erosion. This suggests that the builders were not only surveyors and designers, but also careful observers of the desert environment. In the end, the Nazca geoglyphs stand as a testament to a sophisticated surveying tradition that operated without the tools typically associated with large-scale engineering. Through a combination of geometric intuition, environmental awareness, and possibly communal ritual planning, the Nazca people produced one of the largest artistic landscapes ever created by a pre-industrial civilization. Yet the central mystery remains unresolved. How could a society without aerial vision design, shapes whose beauty and symmetry are fully revealed only from the sky? And until new evidence emerges, the surveying techniques behind the Nazca lines remain one of the most fascinating and enigmatic technological achievements of the ancient world. How do you think the Nazca people managed to create such enormous drawings with nearly perfect precision, even though they could not see them from above? Share your thoughts or theories in the comments below. Roman concrete, known in Latin as opus cementitium, represents one of the most remarkable engineering achievements of the ancient world. Developed more than 2,000 years ago, this material allowed Roman builders to construct harbors, temples, aqueducts, domes, and fortifications that still stand today across Europe and the Mediterranean. While modern concrete structures often deteriorate within decades due to corrosion, cracking, and environmental stress, many Roman concrete structures have survived for nearly 2 millennia. The Pantheon in Rome, with its enormous unreinforced concrete dome spanning more than 40 meters, remains one of the most iconic examples of this technology. Similarly, ancient Roman harbors and seawalls built along the Mediterranean coast continue to endure constant exposure to salt water. The extraordinary durability of these structures has long fascinated engineers and archaeologists, raising a compelling question. How did a civilization without modern chemistry, industrial machinery, or advanced structural analysis create a building material that sometimes outperforms modern concrete? The basic ingredients of Roman concrete appear deceptively simple. The mixture typically included lime, volcanic ash known as pozzolana, water, and fragments of stone or brick used as aggregate. Yet despite the simplicity of these components, the chemical behavior of Roman concrete is surprisingly complex. Unlike modern Portland cement concrete, which tends to weaken over time, as chemical reactions and environmental factors degrade its internal structure, Roman concrete often appears to become stronger with age, and studies of ancient samples have revealed that mineral reactions continue inside the material long after construction is completed. When water penetrates the concrete, especially in marine environments, it can trigger slow chemical reactions between lime and volcanic ash. These reactions gradually form crystalline minerals that fill microscopic cracks and strengthen the internal structure. Instead of breaking down, the material can become denser and more stable over centuries. This process is closely related to what scientists describe as the self-healing behavior of Roman concrete. Many ancient structures show evidence that cracks formed long ago have naturally sealed themselves over time. When fractures occur, water enters the concrete and interacts with remaining lime particles and volcanic ash. Yes, this interaction produces new mineral crystals that slowly grow within the cracks, effectively repairing the damage. In modern engineering, researchers are only beginning to develop similar self-healing concrete technologies using advanced additives or specialized bacteria. Yet Roman builders appear to have achieved a comparable effect using natural materials and empirical knowledge. The presence of lime fragments embedded within the concrete mixture may play an important role in this process, acting as chemical reservoirs that react when water penetrates the structure. One of the most astonishing applications of Roman concrete can be found in marine construction. Throughout the Mediterranean, ancient Roman ports, breakwaters, and harbor foundations were constructed directly in seawater. So modern concrete structures exposed to salt water typically suffer severe deterioration due to chemical corrosion. But Roman marine concrete behaves in a very different way. When seawater penetrates Roman concrete, it interacts with the volcanic ash to produce rare crystalline minerals such as aluminum tobermarite and philipsite. These minerals gradually grow within the concrete, reinforcing its internal structure and making it increasingly resistant to chemical damage. In other words, the interaction between seawater and Roman concrete can actually strengthen the material rather than destroy it. This unusual chemical process has drawn intense scientific interest because it suggests that Roman builders created a material capable of evolving and improving over time. And Roman engineers also demonstrated remarkable ingenuity in the way they used this material in architecture. In monumental structures such as the Pantheon, builders carefully adjusted the composition of the concrete to control weight and structural stability. Heavy aggregates were used in the lower layers of walls and foundations, while lighter volcanic stones, such as pumice, were used in the upper sections of domes. This gradual reduction in weight allowed enormous structures to remain stable without steel reinforcement. The Pantheon's dome, for example, remains the largest unreinforced concrete dome ever built, even by modern standards. Such achievements indicate that Roman builders possessed a sophisticated understanding of construction techniques, even if they lacked formal mathematical models or modern engineering calculations. Yet despite decades of research into Roman concrete, one of the most intriguing aspects of this technology remains unresolved. The exact formula and production methods used by the Romans have not been fully reconstructed. Scientists today understand many of the ingredients used in Roman concrete, but the precise proportions, mixing processes, and construction techniques remain uncertain. Small variations in the ratio of lime to volcanic ash can significantly affect the chemical reactions that occur within the material. Ancient texts written by Roman authors such as Vitruvius describe the use of volcanic ash in construction, but these descriptions are often incomplete or vague, offering little guidance on exact quantities or preparation methods. Recent scientific studies have introduced an additional layer of mystery by suggesting that Roman builders may have used a technique known as hot mixing. In this method, quicklime may have been mixed with other materials while still at extremely high temperatures. This process could produce lime fragments embedded throughout the concrete mixture. These fragments, once exposed to water through small cracks, can dissolve and react to form new crystals that seal the cracks. Such a mechanism would explain the remarkable self-healing properties observed in many ancient structures. However, recreating this exact process in modern laboratories has proven extremely challenging, and researchers have yet to fully reproduce the same long-term durability seen in Roman concrete. And another factor complicating attempts to replicate Roman concrete is the unique geological composition of the volcanic ash used by Roman builders. Much of the most effective pozzolana came from volcanic regions near the Bay of Naples, particularly around Pozzuoli. This ash contains a specific combination of minerals that reacts chemically with lime in ways that may be difficult to reproduce using volcanic materials from other regions. Even when modern scientists use ash from the same geological areas, experimental mixtures often fail to replicate the exact mineral formations found in ancient samples. This suggests that additional variables, such as mixing temperature, curing conditions, or construction methods, may have played critical roles in the final properties of the material. Furthermore, the knowledge behind Roman concrete may have been largely practical rather than theoretical. Ancient builders likely relied on experience passed down through generations of craftsmen rather than precise, written formulas. Construction techniques may have varied between regions and projects, adapting to local materials and environmental conditions. As the Roman Empire declined and its building traditions gradually disappeared, much of this empirical knowledge may have been lost. Without detailed documentation, modern researchers must rely on archaeological evidence and microscopic analysis of surviving structures to reconstruct the technology. Today, scientists continue to study Roman concrete using advanced imaging techniques, chemical analysis, and experimental reconstructions. By examining the mineral structures formed within ancient samples, researchers hope to uncover the precise processes that allowed this material to remain stable for thousands of years. The potential benefits of such discoveries are enormous. Modern concrete production is responsible for a significant portion of global carbon dioxide emissions, and creating a more durable, longer-lasting form of concrete could dramatically reduce the environmental impact of construction. If the secrets of Roman concrete can be fully understood, they may inspire new building materials that are both more sustainable and far more resilient. For now, however, the full formula of Roman concrete remains partially hidden in the past. Despite centuries of study and modern scientific technology, researchers have yet to completely replicate the extraordinary durability achieved by Roman engineers. This lingering mystery serves as a powerful reminder that ancient civilizations sometimes possessed practical knowledge that modern science is still striving to rediscover. Roman concrete is therefore more than a construction material. It is a technological legacy that continues to challenge our understanding of ancient engineering and the limits of modern materials science. What do you think was the true secret behind Roman concrete? The material formula, the hot mixing technique, or perhaps a lost construction method that disappeared over time? Share your thoughts in the comments below. Across the arid landscapes of northeastern Iran, near the borderlands historically connected to the region of Sistan, stands one of the oldest surviving wind-powered technologies on Earth, the Nashtifan windmills. Known as the Nashtifan vertical windmills, these remarkable structures have been harnessing the power of desert winds for more than 1,000 years. Their origins likely date back to somewhere between the 7th and 9th centuries, placing them among the earliest known examples of wind energy engineering in human history. At first glance, the windmills appear deceptively simple, clusters of tall mud brick walls rising above the desert terrain, housing rotating wooden mechanisms that grind grain. Yet beneath this apparent simplicity lies a sophisticated system of environmental adaptation, mechanical ingenuity, and construction techniques that continue to puzzle engineers and historians alike. Unlike the more familiar windmills of medieval Europe, which rely on horizontal axis rotors that must constantly turn to face the wind, the Nashtifan windmills operate on a completely different principle. Their rotors are mounted on a vertical axis, meaning the spinning shaft runs straight up and down, rather than horizontally. This unusual configuration allows the windmills to operate continuously without needing to rotate toward the direction of the wind. The blades are arranged in a semicircular pattern around a vertical shaft, and the entire rotor sits within thick earthen walls that act as aerodynamic guides. These walls contain carefully placed openings that channel the powerful desert winds into the rotating blades from a single direction, while shielding the opposite side from resistance. The result is a remarkably efficient system that converts the region's persistent seasonal winds, particularly the famous 120-day winds of Sistan, into rotational energy capable of grinding grain for local communities. What makes this even more intriguing is that the engineers who designed these machines had no formal understanding of aerodynamics as it would be defined centuries later. Instead, the layout appears to be the product of generations of observation and empirical experimentation, refined gradually until it achieved a balance between power, stability, and durability. The mechanical system inside the windmills is also surprisingly straightforward. The vertical shaft, connected to the rotor, extends downward through the structure and links directly to millstones positioned on the floor below. As the wind turns the blades, the shaft rotates the upper millstone against a stationary lower stone, crushing wheat and other grains into flour. The entire mechanism relies primarily on wooden components, joined with simple mechanical fittings rather than complex metal gears. Despite this simplicity, the system proved reliable enough to remain functional for centuries, and in some cases, the windmills continued operating into the modern era. This endurance highlights one of the most extraordinary aspects of the Nashtifan windmills: their ability to survive in one of the harshest environments imaginable. The region is exposed to relentless winds, abrasive sandstorms, and extreme temperature fluctuations, conditions that would typically degrade structures built from fragile materials. Yet the windmills have persisted for over a millennium, a fact that leads directly to one of their most fascinating and still unresolved mysteries: the remarkable durability of their construction materials. Most of the structures are built primarily from mud brick and compacted clay, materials that are generally considered vulnerable to erosion. In desert climates, strong winds carrying sand particles can gradually wear away surfaces, while rare but intense rainfall events can dissolve poorly protected earthen walls. For this reason, many archaeologists initially assumed that ancient mud brick structures should deteriorate rapidly without constant reconstruction. However, the windmills of Nashtifan challenge this assumption in dramatic fashion. Many of their structural walls have remained standing for centuries, and some appear to have survived with only intermittent maintenance. The secret to this resilience is not yet fully understood. Researchers suspect that the builders may have used a specialized mixture of clay combined with organic fibers or mineral additives that improved the material's resistance to cracking and erosion. Another possibility is that the orientation of the walls themselves was designed to minimize direct exposure to the most destructive wind currents, effectively turning the architecture into a passive protective system. The thick walls surrounding each rotor chamber also act as stabilizing masses, absorbing vibrations generated by the spinning blades and preventing structural fatigue. Even the surfaces of the mud brick appear to have been shaped and smoothed in ways that reduce turbulence and sand abrasion. Despite modern analysis, no definitive formula for the original construction mixture has been identified, leaving open the possibility that a locally refined building tradition, passed down orally rather than documented in written records, contained knowledge that has since been partially lost. The mystery deepens when one considers that the windmills were not isolated experimental structures, but part of an entire architectural complex, carefully arranged along a ridge exposed to the strongest winds. But the placement suggests that ancient builders understood regional wind patterns with remarkable precision. By constructing the windmills along the crest of a hill, they maximized exposure to the prevailing seasonal winds, while also allowing the thick earthen walls to act as natural wind funnels. This combination of environmental awareness and engineering practicality indicates a sophisticated relationship between technology and landscape. In many ways, the Nashtifan windmills represent an early form of renewable energy infrastructure, an ancient system designed to harvest natural forces without relying on fuel or complex industrial materials. Yet their continued survival raises broader questions about technological continuity and lost craftsmanship. And if such durable mud brick structures could be built more than 1,000 years ago in a remote desert settlement, why do modern reconstructions sometimes struggle to replicate their longevity? And how did early builders, working without modern structural theory, manage to achieve a balance between aerodynamic efficiency and architectural stability that allowed these windmills to operate for centuries? Some scholars believe that the answer lies in the cumulative knowledge of local craftsmen who refined the design over generations, gradually improving materials and construction techniques through observation and experience. Others argue that the windmills may reflect a broader technological tradition that once spread across parts of Central Asia and the Middle East, but later disappeared as new technologies replaced older ones. Whatever the explanation, the Nashtifan windmills remain one of the most compelling examples of ancient environmental engineering. Their spinning blades, turning slowly against the desert sky, represent not only an early chapter in the history of wind power, but also a reminder that technological innovation often emerges from a deep understanding of local conditions. The enduring mud brick walls surrounding the mechanisms, still standing after centuries of sandstorms, continue to provoke curiosity among archaeologists and engineers alike. They suggest that within the humble materials of earth and wood may lie a forgotten mastery of sustainable design, a knowledge system developed long before modern engineering existed and perhaps not yet fully rediscovered. What do you think truly allowed the Nashtifan windmills to survive for more than 1,000 years in the harsh desert winds and sand? Was it simply the accumulated experience of ancient craftsmen, or could there have been a more advanced engineering tradition that we still do not fully understand today? Share your thoughts in the comments below. The Angkor hydraulic engineering system is widely regarded as one of the most ambitious and sophisticated water management networks ever constructed in the ancient world. Developed by the Khmer civilization between roughly the 9th and 14th centuries, this enormous hydraulic infrastructure transformed the landscape of what is now northwestern Cambodia into a vast engineered environment designed to control, store, and distribute water across hundreds of square kilometers. At the heart of this system was the ancient urban complex of Angkor, a region that once supported one of the largest pre-industrial populations on Earth. Modern archaeological surveys using satellite imagery, LIDAR scanning, and ground excavation have revealed that Angkor was not simply a city surrounded by temples, but a carefully designed hydraulic landscape composed of immense reservoirs known as barae, long artificial canals, earthen embankments, spillways, and intricate water control structures. Together, these elements formed a massive network capable of capturing seasonal monsoon rains, redistributing water across agricultural lands, and sustaining urban life during prolonged dry seasons. What makes this system particularly remarkable is not only its immense scale, but the extraordinary engineering precision embedded within its design, precision that continues to puzzle modern scientists and engineers. The Khmer engineers who built Angkor operated in a challenging tropical environment characterized by dramatic seasonal contrasts. During the monsoon months, enormous volumes of water could flood the region. Not while during the dry season, rainfall nearly disappeared. To survive and flourish under these conditions, the builders of Angkor developed a hydraulic strategy that essentially transformed the landscape into a giant water regulation machine. Enormous reservoirs such as the West Barae and East Barae were constructed to capture monsoon waters, while long canals distributed that water throughout the surrounding plains. These reservoirs were not small ponds or irrigation basins. Some stretched several kilometers in length and could store tens of millions of cubic meters of water. Their perfectly straight embankments and rectangular geometry suggest careful planning and surveying, raising immediate questions about how ancient engineers achieved such accuracy without modern mapping technologies. The Barae were connected through a network of canals that extended outward toward agricultural zones, linking temples, settlements, and farmland into a single integrated hydraulic environment. Water could flow through this network gradually, feeding rice fields and stabilizing groundwater levels across the Angkor region. Yet among all the impressive features of the Angkor hydraulic network, one aspect stands out as particularly mysterious to modern researchers: the extraordinary precision in the slope of the canals. In any large irrigation system, controlling the gradient of water channels is critically important. If a canal is too steep, water flows too quickly and erodes the channel walls, destroying the structure over time. If it is too flat, water stagnates or fails to move at all. The modern irrigation systems rely on advanced surveying instruments, laser leveling equipment, and detailed topographic mapping to maintain the correct gradient across long distances. However, the canals of Angkor, some stretching for kilometers across subtle terrain, appear to have been constructed with an incredibly delicate balance of elevation differences. In some cases, the vertical drop along an entire canal may measure only a few tens of centimeters over distances of several kilometers. Achieving such accuracy without modern instruments represents one of the most puzzling technical mysteries of the Angkor system. Archaeological and geomorphological studies have shown that many Angkor canals maintained a consistent gradient that allowed water to flow slowly and predictably through the network. This controlled movement prevented destructive flooding, while ensuring that irrigation water could reach distant agricultural fields. The precision required for such engineering is astonishing. Even a small miscalculation during construction could have disrupted the entire hydraulic flow, either causing water to pool uselessly or allowing it to rush through the system with damaging force. Yet the surviving channels suggest that Khmer engineers somehow mastered a method of surveying the land with remarkable subtlety. Scholars have proposed several theories to explain how this might have been achieved. Some believe that simple but effective tools such as water level measuring devices, sighting rods, or wooden leveling frames could have been used in combination with careful observation of natural terrain. Others argue that the builders may have relied on long-term empirical knowledge gained through generations of hydraulic experimentation in rice agriculture. Still, no clear archaeological evidence has yet revealed the exact techniques used to measure and maintain these gradients across such vast distances. The mystery deepens when researchers consider the sheer scale of the network. Angkor's canals were not isolated engineering projects, but components of a much larger system linking reservoirs, rivers, and floodplains. Water flowing from upland catchment areas could be directed into storage basins, then released gradually into downstream canals, depending on seasonal conditions. In effect, the entire Angkor landscape functioned as a giant hydraulic circuit. Maintaining precise canal slopes across such a system would have required careful coordination between multiple construction phases and possibly thousands of workers. It would also have required a deep understanding of hydrology, soil behavior, and seasonal water patterns. Yet the Khmer civilization left behind very few written records describing these technical practices. As a result, modern scientists must reconstruct the system indirectly through field measurements, excavation, and computer modeling. Another intriguing feature of the Angkor hydraulic network is the relationship between practical engineering and symbolic cosmology. Many reservoirs and canals appear to align with temple complexes and urban layouts in ways that reflect religious concepts drawn from Hindu and Buddhist cosmology. The Baray reservoirs, for example, may have symbolized the cosmic ocean surrounding the mythical Mount Meru, the sacred center of the universe in classical Indian cosmology. Temples were often positioned on artificial islands or near canal intersections, creating a landscape that blended hydraulic engineering with spiritual meaning. This fusion of symbolism and infrastructure suggests that Angkor's water system was not purely utilitarian, but also part of a broader cultural and cosmological design. However, the exact balance between practical irrigation needs and symbolic intentions remains a subject of ongoing debate among archaeologists. Modern LiDAR technology has revolutionized the study of Angkor by revealing hidden features beneath dense forest cover, and these scans show that the hydraulic system extended far beyond the monumental temples typically associated with Angkor. Vast grids of channels, embankments, and ponds once connected rural settlements to the central reservoirs, creating a landscape engineered on a scale comparable to some modern metropolitan regions. This discovery reinforces the idea that Angkor was not simply a ceremonial center, but a massive urban ecosystem sustained by sophisticated water management. Yet it also raises further questions. If the system was so carefully designed, why did it eventually fail? Evidence suggests that during the later centuries of the Khmer Empire, climate fluctuations produced cycles of intense drought, followed by destructive floods. These extreme conditions may have overwhelmed sections of the hydraulic network, but sediment buildup and structural damage could have disrupted water flow, gradually reducing the efficiency of irrigation systems that the city depended upon. In the end, the Angkor hydraulic system remains one of the most impressive environmental engineering achievements of the ancient world. It demonstrates that the Khmer civilization possessed a deep understanding of hydrology, landscape planning, and large-scale engineering. However, the precise slope of the canals, which allowed water to flow steadily across very long distances, still remains an unresolved question. Without modern surveying tools or advanced measuring technology, Angkor's engineers somehow created a hydraulic network with remarkable accuracy. For this reason, the system is not only an ancient engineering monument, but also a major mystery that scientists continue to study today. How do you think ancient Khmer engineers were able to calculate the slope of canals stretching for kilometers with near-perfect precision, without modern surveying instruments? Share your thoughts or theories in the comments below. High on the windswept Altiplano of western Bolivia, near the southern shore of Lake Titicaca, lies one of the most puzzling archaeological sites ever discovered, Puma Punku, a monumental complex associated with the ancient Tiwanaku civilization. Dating back roughly 1,500 years, this site has long fascinated archaeologists, engineers, and historians because of one astonishing feature above all others: the extraordinary precision with which its massive stone blocks were cut and shaped. Unlike many other ancient ruins where weathering and irregular construction are common, the stones of Puma Punku appear almost impossibly refined. Their surfaces are flat, their edges crisp, and their geometry so exact that many observers have compared them to products of modern mechanical fabrication. The site's construction raises a profound question that continues to challenge scientific understanding. How did an ancient civilization, working without iron tools, advanced machinery, or written engineering manuals, achieve such remarkable levels of stoneworking precision? The stones themselves are impressive in both size and material. Many of the largest blocks are made from red sandstone, some weighing over 100 tons, while the more intricately carved pieces are often made from andesite, a dense volcanic rock that is significantly harder than sandstone and notoriously difficult to shape. Andesite is so tough that even modern masons must rely on hardened steel tools or power equipment to carve it efficiently. Yet at Puma Punku, the andesite blocks display a level of refinement that seems to defy the technological limitations typically attributed to the Tiwanaku culture. Their surfaces are perfectly planar, their edges sharply defined, and many of their internal angles approach exact right angles. Some stones are so precisely finished that when two are placed together, the joint between them becomes nearly invisible. Among the most iconic features of Puma Punku are the famous H-shaped blocks. These stones are carved with remarkable uniformity, featuring intricate recesses, channels, and rectangular cutouts that appear carefully standardized. Archaeologists have noted that many of these blocks are nearly identical in size and design, suggesting that the builders followed a carefully planned architectural system. The repetition hints at a kind of modular construction approach, in which individual components were crafted to fit together in a predetermined arrangement. Such standardization is extremely rare in ancient stone architecture and implies a level of measurement accuracy and construction planning far more sophisticated than previously assumed for pre-Columbian societies. However, the most mysterious aspect of Puma Punku's engineering lies in the remarkably precise grooves and drilled holes carved into many of the stones. These features stand out because of their smoothness, symmetry, and geometric perfection. Across several andesite blocks, one can observe narrow channels cut into the surface with straight edges and consistent depth. In some cases, these grooves intersect at clean angles, forming geometric patterns that appear almost machine-made. Even more striking are the perfectly circular holes drilled into the stone. These holes are uniform in diameter and remarkably smooth along their interior walls, suggesting a controlled drilling process rather than simple hammering or chiseling. The presence of these holes has generated intense debate among researchers. Some of them resemble the marks left by rotational drilling tools, producing spiraling patterns that imply the use of a rotating drill bit. Modern observers immediately recognize similarities to holes produced by contemporary mechanical drills. Yet according to mainstream archaeological understanding, the Tiwanaku civilization did not possess iron or steel tools capable of maintaining such rotational drilling pressure against hard andesite, though their available metals were primarily copper or bronze alloys, which are significantly softer and typically unsuitable for cutting dense volcanic rock with such precision. This contradiction has led scholars to explore several possible explanations. One hypothesis suggests that ancient craftsmen used stone tools harder than the material they were shaping, combined with abrasive sand and water to slowly grind away the rock. Over long periods, such a method could theoretically produce smooth grooves and holes. Another possibility involves the use of bow drills, a tool known in many ancient cultures in which a string-driven spindle rotates a drill bit rapidly back and forth. When combined with abrasive materials, such devices could gradually bore into stone surfaces. However, even with these techniques, and reproducing the exact smoothness and consistency seen in Puma Punku remains extremely difficult. Experimental archaeologists attempting to replicate these features often discover that achieving the same level of precision requires enormous time and effort. Some modern tests suggest that it would take many hours or even days to produce a single hole comparable to those found at Puma Punku using primitive tools. This raises an intriguing possibility. Either the Tiwanaku builders invested immense labor into their stoneworking techniques, or they possess specialized methods that have not yet been fully understood. The grooves carved into the stones also appear to have served structural or mechanical purposes. Many channels seem designed to hold metal clamps that once connected neighboring blocks. Now, archaeologists have indeed discovered traces of T-shaped metal fasteners embedded in certain stone joints. These clamps were likely made from copper-based alloys poured into carved recesses to bind the stones together. The precision required to create these clamp sockets is extraordinary. Each recess had to match its counterpart perfectly in order to secure the blocks tightly, demonstrating not only stone-cutting expertise, but also advanced knowledge of structural reinforcement. Another factor that deepens the mystery is the transportation and placement of these precisely carved stones. Some of the largest blocks were quarried from locations many kilometers away. The red sandstone likely originated from quarries around 10 kilometers from the site, while the andesite used for the most intricate carvings may have been transported from sources up to 90 kilometers away. Moving stones weighing tens of tons across rugged terrain at an altitude exceeding 3,800 meters above sea level would have required sophisticated logistical planning. Yet no definitive evidence of the transport methods has been found. Taken together, the precise grooves, drilled holes, and geometric carvings of Puma Punku present a remarkable example of ancient engineering. They reveal a level of craftsmanship that challenges conventional assumptions about the technological capabilities of early Andean civilizations. While scholars generally agree that the Tiwanaku people were highly skilled stoneworkers, the exact techniques they used remain uncertain. The mysterious drilling marks, the perfectly cut channels, and standardized architectural blocks suggest that their methods may have been more advanced, or at least more refined, than previously imagined. Today, Puma Punku stands as both an archaeological treasure and a technological puzzle. Its stones continue to inspire debates among scientists, historians, and engineers, each seeking to understand how such precision was achieved in a world without modern machines. Whether the answer lies in lost techniques, extraordinary patience, or a deeper knowledge of materials and geometry, one thing remains clear. The stone cutting of Puma Punku represents one of the most extraordinary achievements of ancient engineering, and its secrets have yet to be fully uncovered. What do you think the ancient Tiwanaku builders used to create the incredibly precise grooves and drilled holes at Puma Punku? Simple tools combined with extraordinary craftsmanship, or a technological method that has been lost over time? Share your thoughts in the comments below. High in the dry coastal desert of northern Peru, overlooking the Casma Valley, stands one of the most remarkable and enigmatic ancient astronomical sites ever discovered in the Americas, the Chankilo Solar Observatory. Built more than 2,300 years ago, around the 4th to 3rd century BCE, this complex represents a level of astronomical understanding that continues to astonish archaeologists and historians alike. Long before the rise of the Inca civilization, and long before written records appeared in the Andes, the builders of Chankilo created what many scholars now consider the earliest known solar observatory in the New World. The site consists of a ceremonial complex, a fortified temple, and most famously, a line of 13 stone towers stretching across the crest of a low hill. And at first glance, these towers appear simple, almost austere, against the barren desert landscape. Yet their placement reveals a sophisticated knowledge of the movement of the sun across the horizon throughout the year. When viewed from carefully constructed observation points to the east and west of the hill, the towers act as markers that track the rising and setting positions of the sun across the annual solar cycle. As the seasons change, the sun appears to move gradually along the horizon, rising and setting between different towers. During the June solstice, the sun rises near the northernmost tower, while during the December solstice, it appears near the southernmost one. On other days of the year, it rises or sets between the intermediate towers, allowing observers to determine the approximate date simply by noting the sun's position relative to the line of structures. In essence, the entire hill functions as a massive solar calendar carved into the landscape. What makes this system particularly extraordinary, and what continues to puzzle scientists, is the astonishing level of astronomical precision embedded in its design. The 13 towers are not spaced randomly, nor are they merely symbolic structures. Detailed archaeological and astronomical studies have demonstrated that their positions correspond closely to the changing azimuth of the sun as it rises and sets across the horizon during the year. When observed from the designated viewing platforms, the gaps between the towers effectively divide the solar year into segments that correspond closely to real seasonal shifts. The accuracy of this arrangement is remarkable. The system allows observers to estimate the day of the year with an error margin of only a few days. For a civilization that possessed no written astronomy, no telescopes, and no known angular measuring instruments, such precision raises profound questions about how the builders were able to calculate these alignments. Achieving this level of accuracy would have required a deep and sustained understanding of solar motion. The apparent path of the sun across the horizon does not remain constant. It gradually shifts northward and southward over the course of the year due to the tilt of Earth's axis. To design a structure that could track this movement, the builders of Chankilo must have conducted careful observations of sunrise and sunset points over many years, possibly over several generations. By recording where the sun appeared along the horizon at different times of the year, they could identify the extreme positions of the solstices as well as the intermediate positions between them. Only after accumulating this knowledge could they determine where towers should be constructed so that the sun would align with them in a predictable and useful way. The engineering challenge was not trivial. The towers had to be placed along a ridge whose orientation allowed clear views of the horizon, and they had to be spaced so that the angular differences between them matched the seasonal shifts in solar position. Even small errors in placement could have disrupted the accuracy of the entire system. Equally intriguing is the presence of two purpose-built observation structures located on opposite sides of the tower line. From the eastern observation point, an observer could watch the sun rise through the gaps between the towers. From the western point, the same system could be used to observe the setting sun. This dual alignment effectively doubled the functionality of the observatory, allowing solar tracking both at dawn and at dusk. Such a design suggests that the builders had a sophisticated awareness not only of solar movement, but also of the importance of observation geometry. They understood that the same line of towers could serve as markers from two different vantage points, greatly enhancing the reliability of the solar calendar. Yet the mysteries of Chankilo extend beyond its astronomical accuracy. Nearby stands a structure known as the Fortified Temple, a complex with thick defensive walls, narrow entrances, and multiple layers of fortification. The presence of what appears to be a defensive stronghold next to an astronomical observatory raises intriguing questions about the social role of the site. Some researchers believe the observatory may have been part of a ceremonial center where solar events were linked to ritual and political authority. In many ancient societies, the ability to predict celestial events carried enormous symbolic power. Leaders who controlled knowledge of the calendar could regulate agricultural cycles, religious festivals, and seasonal labor. And others suggest the fortified complex may reflect periods of conflict or the need to protect a sacred or politically important location. The broader cultural context also adds to the intrigue. The civilization responsible for Chankilo predates many of the famous Andean cultures that later dominated the region. Unlike the Maya or other literate civilizations of the ancient world, these people left no written records explaining their astronomical knowledge. Instead, the evidence of their scientific understanding survives only in stone alignments, architectural orientation, and the careful geometry of the site itself. This absence of written explanation makes it difficult for modern researchers to reconstruct the intellectual processes that led to the creation of the observatory. Despite decades of research, Chankilo continues to raise fundamental questions about the development of scientific knowledge in ancient societies. How did its builders discover the precise limits of the sun's annual movement along the horizon? How many years of observation were required before they felt confident enough to construct permanent markers? What methods did they use to measure angles and distances across the landscape? Without compasses, precision surveying tools, or written mathematical systems, the creators of Chankilo achieved a level of astronomical accuracy that rivals many later ancient observatories around the world. Their achievement demonstrates that careful observation, patience, and accumulated generational knowledge can produce sophisticated scientific systems even in the absence of advanced technology. Today, the Chankilo Solar Observatory stands as a silent testament to the ingenuity of ancient Andean peoples. Rising above the desert landscape, the 13 towers still trace the sun's annual journey just as they did more than 2 millennia ago. For modern observers, the site offers a rare glimpse into the scientific curiosity and observational discipline of a prehistoric culture whose achievements remain only partially understood. Even now, as archaeologists continue to study the site and refine their understanding of its alignments, the extraordinary precision of its solar design remains one of the most compelling mysteries in the history of ancient astronomy. How do you think an ancient civilization without telescopes or modern measuring instruments was able to build such a precise solar observation system like Chankilo? Share your thoughts in the comments below. Inca polygonal masonry stands as one of the most astonishing achievements of ancient engineering, a construction technique that continues to fascinate archaeologists, engineers, and historians alike. Across the highlands of the Andes, especially in cities such as Cusco, Ollantaytambo, and the monumental fortress complex of Sacsayhuaman, massive stone walls built by the Inca Empire display a level of precision and craftsmanship that seems almost impossible for a pre-industrial civilization. These walls are composed of irregularly shaped, multi-angled stones, fitted together so perfectly that no mortar or binding material was needed to hold them in place. Despite earthquakes, erosion, and the passage of centuries, many of these structures remain standing today in remarkable condition, and often outperforming later colonial buildings constructed with more modern techniques. The mystery lies not only in the beauty of the masonry itself, but also in the technological questions it raises about how such work could have been achieved with the tools and knowledge available to the Inca more than 500 years ago. One of the most striking features of Inca polygonal masonry is the extraordinary precision with which the stones were shaped and fitted together. Each block is unique, often containing many sides and angles, and designed to interlock with the surrounding stones like pieces of an elaborate three-dimensional puzzle. A famous example can be found in Cusco's Hatun Rumiok Street, where a single stone with 12 distinct angles fits seamlessly into the surrounding wall. And such stones were not cut into regular rectangular shapes, but instead carefully sculpted so that each surface matched the contours of the stones beside it. The result is a wall with a flowing organic geometry rather than the rigid symmetry seen in many other ancient stone constructions. This level of craftsmanship suggests an extremely careful process of shaping, testing, and refining each block until it achieved a nearly perfect fit with its neighbors. Even today, visitors often remark that the joints between stones are so tight that a thin blade or sheet of paper cannot easily be inserted between them. Equally remarkable is the fact that these walls were built entirely without mortar. Most ancient civilizations relied on mud, lime, or other binding materials to secure stones in place. But the Inca chose a different approach. Now, instead of gluing the stones together, they relied on precise stone shaping and the immense weight of the blocks themselves. The stones were cut so accurately that they locked into one another, distributing structural forces across many surfaces at once. This design created an extremely stable structure, capable of withstanding the frequent earthquakes that occur in the Andes. When seismic vibrations pass through the ground, the stones can shift slightly and then settle back into position without collapsing. This flexible stability has allowed many Inca walls to survive for centuries, even while later buildings constructed nearby with mortar and bricks have crumbled. The technique demonstrates a deep intuitive understanding of structural behavior, as suggesting that the Inca builders had developed highly effective engineering solutions through generations of experience. However, one of the greatest puzzles surrounding Inca polygonal masonry involves the transportation and handling of the enormous stones used in these constructions. Some blocks weigh dozens of tons, and in certain sites, such as Sacsayhuaman, stones weighing well over 100 tons were carefully placed into walls with astonishing precision. The challenge becomes even more intriguing when considering that the Inca civilization did not use wheeled vehicles for heavy transport and lacked large draft animals like horses or oxen. The only domesticated animals available were llamas and alpacas, which were incapable of pulling massive loads. But scholars believe that the stones were moved using large groups of laborers, ropes made from plant fibers, wooden rollers, and carefully constructed earthen ramps. Yet the exact methods remain uncertain, and the logistical coordination required to move and position such enormous blocks across mountainous terrain continues to raise questions about the organizational capabilities of the Inca state. Among all the mysteries of this construction technique, perhaps the most fascinating involves the tools used by the Inca stoneworkers themselves. Archaeological evidence suggests that the Inca did not possess iron or steel tools comparable to those used in later periods of history. Instead, they primarily relied on hammerstones made from hard rock, as well as tools crafted from copper or bronze alloys. Compared to modern steel cutting tools, these materials are relatively soft, especially when working with extremely hard stones such as granite or andesite, the very materials commonly used in Inca construction. At first glance, it seems almost impossible that such simple tools could produce the extraordinary precision seen in Inca walls. Yet the evidence clearly shows that these stones were carefully shaped, smoothed, and fitted with remarkable accuracy. Researchers believe that the process of shaping the stones may have involved a combination of repeated hammering, grinding, and abrasion techniques. Workers likely used harder stones as hammer tools to chip away at the surface of the blocks, gradually refining their shape through thousands of careful strikes. Sand and water may have been used as abrasive materials to grind surfaces smooth and adjust the fit between stones. Rather than cutting stones quickly, as modern machines do, Inca builders may have relied on slow, incremental shaping, testing the fit of each stone repeatedly against its neighbors. When a block was placed in position, its contact points with surrounding stones could be marked or worn down slightly until the surfaces matched perfectly. Over time, this iterative process would produce the incredibly tight joints seen in surviving walls today. Even so, the level of precision achieved by these methods remains astonishing. The ability to shape multi-ton stones into complex polygonal forms ensure that each surface aligns perfectly with adjacent stones and maintain overall structural stability across an entire wall requires not only patience, but also a deep understanding of geometry and material behavior. Yet the Inca left behind no written manuals describing their engineering techniques, and the knowledge may have been transmitted orally among specialized craftsmen. As a result, modern researchers can only reconstruct possible methods by studying tool marks, experimental archaeology, and comparisons with other ancient stoneworking traditions. Another aspect that remains unclear is how the builders measured and planned the complex shapes required for polygonal masonry. Unlike rectangular stone blocks, which can be measured using simple straight edges, irregular polygonal stones require careful spatial reasoning to ensure that multiple surfaces align simultaneously. Some researchers propose that the Inca used direct physical testing rather than abstract measurements, repeatedly placing stones into position and removing small amounts of material until the desired fit was achieved. Others suggest that the builders may have used cords, wooden templates, or simple geometric guidelines to guide the shaping process. Whatever the method, the final result demonstrates an extraordinary level of craftsmanship that continues to impress engineers even in the age of advanced technology. Ultimately, Inca polygonal masonry represents more than just a construction technique. It is a testament to the ingenuity and adaptability of a civilization that thrived in one of the most challenging environments on Earth. Without steel tools, wheeled transport, or written engineering manuals, the Inca managed to create structures of remarkable strength, beauty, and resilience. The walls of Cusco and the terraces of the Sacred Valley stand not only as architectural achievements, but also as enduring reminders of a sophisticated technological tradition whose full secrets may never be completely understood. Even today, as modern engineers analyze these ancient structures with lasers, computer models, and geological studies, the question remains: how did craftsmen, using such simple tools, achieve such extraordinary precision? How do you think the Inca were able to cut and fit these massive stones with such incredible precision, using only simple tools? Share your thoughts in the comments below. The technology behind Sanxingdui bronze casting remains one of the most fascinating and mysterious achievements of ancient metallurgy. Hidden for thousands of years beneath the soil of the Sichuan Basin in southwestern China, the archaeological site of Sanxingdui revealed a civilization whose bronze working capabilities appeared unexpectedly advanced when the first major excavations took place in the 20th century. When archaeologists uncovered the famous sacrificial pits filled with massive bronze masks, towering statues, elaborate ritual objects, and intricate symbolic artifacts, it immediately became clear that the craftsmen of this ancient Shu civilization possessed metallurgical knowledge far beyond what historians had previously assumed for that region and time period. The artifacts date roughly to the late 2nd millennium BCE, a time when bronze casting was already well developed in the central plains of China during the Shang dynasty. Yet the bronzes of Sanxingdui display both a scale and a technological complexity that appear strikingly different from anything produced in the more familiar centers of early Chinese civilization. One of the most astonishing aspects of Sanxingdui metallurgy is the sheer size and structural complexity of the bronze objects themselves. Among the discoveries is a monumental bronze statue of a standing human figure more than 2.5 meters tall, weighing well over 100 kilograms, making it the largest known bronze human figure from ancient China. There are also enormous bronze masks with exaggerated facial features, and some with eyes that project outward dramatically from the face, and the remarkable bronze tree, an intricate structure nearly 4 meters high with branching arms, decorated with birds, dragons, and symbolic ornaments. Producing objects of this scale in bronze requires precise control of furnace temperatures, carefully prepared molds capable of withstanding intense heat, and an understanding of how molten metal behaves as it cools and contracts. Even today, large-scale casting requires careful engineering, and the existence of such objects from more than 3,000 years ago suggests a sophisticated metallurgical tradition that had already matured long before the artifacts were buried in the sacrificial pits. Another remarkable element of Sanxingdui bronze technology is the method by which many artifacts appear to have been constructed from multiple, separately cast components. Detailed examinations of statues, masks, and ritual objects reveal that craftsmen often cast individual sections independently and later joined them together to form a unified structure. Arms, torsos, decorative protrusions, and elaborate ornaments were produced in separate molds and then assembled with astonishing precision. The seams between these sections are often nearly invisible, suggesting that ancient artisans had developed techniques to control metal contraction and alignment with extraordinary accuracy. Such multi-stage casting implies a deep understanding of both metallurgy and structural design, because each component would have had to fit perfectly with the others after cooling. This kind of modular casting strategy allowed Sanxingdui craftsmen to create highly complex forms that would have been extremely difficult to produce as single solid castings. Equally intriguing is the unusual composition of the bronze alloy itself. Scientific analysis of Sanxingdui artifacts shows that many objects were produced using a bronze mixture that includes copper, tin, and unusually high proportions of lead. In some cases, the lead content is significantly higher than that found in contemporary bronzes from other regions of China. This composition lowers the melting point of the metal and allows molten bronze to flow more easily into intricate mold cavities, making it particularly useful for casting detailed shapes and thin decorative features. However, high lead content can also make the finished metal more brittle and difficult to control structurally. The fact that Sanxingdui artisans were able to cast such large and complex objects, despite this challenge, suggests they possessed a refined understanding of how to manipulate alloy properties to achieve the desired balance between fluidity and stability. Yet historical records from later Chinese dynasties provide almost no direct descriptions of these techniques, leaving modern researchers to reconstruct the process entirely from physical evidence. Perhaps the most intriguing mystery surrounding Sanxingdui bronze technology lies in the design and construction of the casting molds themselves. Now, archaeologists generally believe that ancient Chinese bronze objects were produced using the piece mold casting technique, in which clay molds were created in multiple segments that could be assembled around a core before molten metal was poured inside. This method was widely used during the Shang dynasty and allowed artisans to produce vessels decorated with complex surface patterns. However, many Sanxingdui artifacts appear far more complex than typical piece mold objects. The dramatic protruding eyes of the bronze masks, the deep three-dimensional structures of statues, and the delicate branching forms of the bronze tree raise serious questions about how the molds were actually constructed. In conventional piece mold casting, removing the mold segments after the metal cools requires careful separation along predetermined lines. If the object contains undercuts, extended projections, or deeply layered forms, the mold could become impossible to remove without breaking either the mold or the object itself. Yet the Sanxingdui artifacts contain exactly these kinds of challenging geometries. For this reason, the precise mold design used by Sanxingdui craftsmen remains one of the most debated subjects in ancient metallurgy research. Some scholars propose that artisans combined piece mold casting with additional techniques such as separately cast attachments or temporary clay supports that were later removed. Others suggest that specialized mold configurations may have been used, possibly incorporating removable internal sections or innovative assembly strategies that have not survived in the archaeological record. Our experimental archaeologists have attempted to reproduce certain Sanxingdui objects using traditional bronze casting techniques, but many reconstructions struggle to replicate the full complexity of the original artifacts. The enormous bronze masks with elongated eyes, for example, present a particularly difficult challenge, as the extended eye structures would require mold segments capable of forming narrow internal channels while still allowing the mold to be removed intact after casting. Even with modern experimental methods, achieving the same results using strictly ancient technologies remains extremely difficult. This suggests that the mold design system employed by Sanxingdui artisans may have included specialized knowledge that has been lost over time. The mystery is compounded by the fact that very few intact molds have been discovered at the site itself. While fragments of clay molds and casting debris have been identified, they do not yet provide a complete picture of the entire manufacturing process. Without full mold assemblies, archaeologists must rely on indirect clues from the metal objects themselves, such as seam lines, casting textures, and microscopic structural patterns within the bronze. These clues indicate that the molds were carefully engineered and precisely aligned before casting began. The complexity of some artifacts implies that multiple casting stages may have been required, possibly involving intermediate steps where partially completed components were combined with new molds to add additional sections. Such a process would require not only technical skill, but also careful planning and coordination among craftsmen. Beyond the technological questions, the unique artistic style of Sanxingdui bronzes adds another layer of mystery. The exaggerated facial features of the masks, with their elongated eyes and monumental expressions, do not resemble the artistic traditions seen in other Bronze Age cultures of China. Instead, they suggest a distinct symbolic system that may have been associated with religious rituals or mythological beliefs of the ancient Shu civilization. The bronze tree, with its layered branches and animal figures, may represent a cosmological concept or a sacred structure connecting the human world with the heavens. If these objects were indeed ritual artifacts, and their unusual forms may have required equally unusual casting methods designed specifically to achieve symbolic shapes rather than practical ones. This could partly explain why the mold designs appear so unconventional compared to typical bronze casting of the era. Another unanswered question concerns the origin of the raw materials used to produce these bronzes. The Sichuan Basin is not widely known as a major early center of copper or tin production. Yet the sheer volume of bronze artifacts discovered at Sanxingdui suggests access to a substantial supply of metal resources. Some researchers believe that extensive trade networks may have transported copper and tin from distant mining regions into the Shu kingdom, while others suggest that previously unknown local sources may have existed in the surrounding mountains. Without clear evidence of mining sites directly linked to Sanxingdui metallurgy, the supply chain behind this remarkable bronze industry remains uncertain. Adding to the mystery is the sudden disappearance of the Sanxingdui culture and its distinctive bronze casting tradition. Archaeological evidence suggests that the civilization declined or transformed sometime around the 11th century BCE. After this period, the extraordinary artistic and technological style seen in Sanxingdui bronzes does not continue in the same form in later regional cultures. While nearby sites such as Jinsha show certain cultural connections, the monumental bronze sculptures and masks characteristic of Sanxingdui largely vanish from the archaeological record. This abrupt shift raises the possibility that the knowledge required to produce these artifacts was lost, abandoned, or intentionally discontinued as political and cultural conditions changed. Overall, the bronze artifacts of Sanxingdui are not only masterpieces of ancient art, but also technological puzzles that remain unsolved. Their monumental scale, complex assembly techniques, unusual alloy composition, and especially the mysterious mold designs challenge modern understanding of Bronze Age manufacturing. Despite decades of research, archaeologists have still not been able to fully recreate the casting process used by the ancient Shu craftsmen. As a result, these artifacts stand as enduring evidence of a sophisticated body of technical knowledge that may have been lost to history. How do you think the craftsmen of the ancient Shu civilization at Sanxingdui were able to create such incredibly complex bronze casting molds more than 3,000 years ago? Share your thoughts or theories in the comments below. The drainage system of Mohenjo-daro stands as one of the most remarkable yet enigmatic engineering achievements of the ancient world. Built more than 4,000 years ago during the height of the Indus Valley civilization, the city reveals a level of urban planning and sanitation infrastructure that appears astonishingly advanced for its time. Unlike many ancient settlements where drainage was improvised or limited to simple ditches, Mohenjo-daro was designed with an integrated sanitation network that ran beneath streets, alongside buildings, and through residential blocks. Nearly every house in the city had access to private bathing areas, and wastewater from these spaces was carefully directed into a complex system of brick-lined drains that ultimately carried waste away from the living quarters of the population. And the sophistication of this system has puzzled archaeologists for decades, not only because of its scale and consistency, but also because it demonstrates a level of engineering knowledge that seems unexpectedly mature for a civilization that flourished more than 2 millennia before the rise of classical Greek and Roman urban engineering. The city itself appears to have been carefully planned around this hydraulic infrastructure. Streets were laid out in an organized grid pattern, and along these streets ran covered drainage channels constructed from standardized baked bricks. Many of these channels were sealed with removable stone or brick slabs, allowing access for cleaning and maintenance, suggesting that the inhabitants of Mohenjo-daro understood the long-term requirements of managing a complex sewer network. Archaeological excavations have revealed that some drains were connected to small settling tanks designed to trap solid waste before it entered the larger municipal channels, a concept strikingly similar to sedimentation systems used in modern wastewater engineering. These details indicate that the builders of Mohenjo-daro were not simply disposing of water, but were actively controlling its flow and cleanliness within an urban environment. Yet among all the extraordinary aspects of this ancient sanitation network, perhaps the most mysterious and technically impressive feature lies in the precision of its gradients. For a drainage system to function effectively across a city, the channels must maintain a carefully calculated slope so that water flows steadily without stagnation. If the slope is too shallow, water will accumulate and cause blockages. If it is too steep, the flow can erode the structure of the channel or leave solid waste behind. Modern sewer systems require precise surveying instruments to calculate such gradients across long distances. However, Mohenjo-daro was built around 2600 BCE, long before the invention of modern surveying tools, yet archaeological measurements show that many of its drains maintain a remarkably consistent incline over considerable lengths. In several excavated streets, the drains descend gradually and smoothly, guiding wastewater away from residential districts with an efficiency that suggests deliberate engineering planning rather than accidental alignment. This precision raises one of the most intriguing technological mysteries associated with the city. Now, how did the engineers of the Indus Valley achieve such accurate gradients without the instruments that modern engineers rely upon today? Scholars have proposed several possibilities. Some suggest that builders may have used simple water leveling techniques, perhaps by observing how water naturally flowed along shallow channels before constructing permanent brick drains. Others speculate that they may have relied on stretched cords, weighted plumb lines, or primitive leveling frames to maintain consistent slopes. Yet despite decades of excavation, no definitive evidence of specialized surveying tools has been discovered in the archaeological record. Without written manuals or deciphered technical texts, the script of the civilization, known as the Indus script, remains undeciphered. Modern researchers are left to infer the knowledge of these ancient engineers only through the structures they left behind. The mystery becomes even deeper when Mohenjo-daro is compared with other great civilizations of the same era. In Mesopotamia, cities such as Ur and Babylon developed impressive irrigation canals and water management systems, yet their urban drainage infrastructure rarely matched the systematic integration seen in the Indus cities. In ancient Egypt, monumental architecture and irrigation technology flourished, but large-scale covered municipal sewer networks comparable to Mohenjo-daro's were not typical features of Egyptian urban design. Even later civilizations with advanced engineering traditions, often relied on simpler drainage solutions within residential districts. This makes the Indus system appear not merely advanced, but unusually comprehensive, raising the possibility that the civilization possessed a sophisticated tradition of hydraulic engineering that has largely vanished from the historical record. Another remarkable aspect of the system is the uniformity of its construction materials. The drains were built from carefully shaped baked bricks produced in standardized proportions, typically following a ratio of 1 to 2 to 4 in thickness, width, and length. This level of standardization implies an organized manufacturing process and possibly centralized regulation of building materials. The bricks themselves were fired at high temperatures, giving them exceptional durability. As a result, sections of the drainage network have survived for more than 4 millennia, despite exposure to flooding, erosion, and environmental change. Some channels were also lined with waterproof materials, suggesting that the builders were aware of the need to protect the masonry from long-term water damage. Such details hint at an advanced understanding of both materials science and structural longevity. Maintenance features further highlight the sophistication of the system. In many locations, archaeologists have identified inspection openings where the covers of drains could be removed to allow cleaning. These access points appear at regular intervals along the channels, implying that routine maintenance was expected and planned for. The existence of these features suggests a level of municipal organization capable of managing public infrastructure across the city. However, this again raises a puzzling question: who coordinated such activities? Unlike many ancient societies, the Indus civilization left behind no monumental inscriptions glorifying kings or administrators. Without deciphered texts, it remains unclear whether the drainage network was managed by centralized authorities, local guilds, or some other form of civic organization. Even more intriguing is the role of household-level filtration systems connected to the larger network. Some houses contained small brick basins or soak pits designed to capture debris before wastewater entered the street drains. This indicates that sanitation practices were integrated not only at the municipal level, but also within individual homes. The concept of separating solid waste from flowing water before it reaches the main sewer channels reflects a remarkably modern understanding of how to prevent clogging and maintain hydraulic efficiency. Such design choices imply that the inhabitants of Mohenjo-daro had practical knowledge derived from experience with water management over generations. Despite its sophistication, the fate of this technology remains one of archaeology's most difficult puzzles. Around 1900 BCE, the urban centers of the Indus Valley began to decline. The reasons are still debated, with theories ranging from climate change and shifting river courses to economic disruptions or gradual social reorganization. As the cities were abandoned or reduced in scale, these complex drainage systems also fell into disuse. What is striking is that comparable urban sanitation systems did not appear widely in many parts of the world for centuries afterward. In some regions, complex sewer networks would not become common again until the era of ancient Rome, more than a millennium later. The drainage system of Mohenjo-daro stands as both a remarkable achievement of ancient engineering and a reminder that technological knowledge can disappear from history. Its carefully calculated slopes, standardized bricks, inspection chambers, and household filtration pits reveal a civilization with an advanced understanding of urban infrastructure. Yet the people who designed this system remain unknown, with their script undeciphered and their engineering knowledge largely reconstructed only through archaeology. Today, the brick-lined channels still reveal the precision of their design, but the knowledge that created them remains one of the enduring mysteries of the ancient world. How do you think the ancient builders of Mohenjo-daro were able to calculate the precise slope of their drainage system more than 4,000 years ago? Was it the result of engineering methods that have been lost to history, or have we simply underestimated their scientific knowledge? Share your thoughts in the comments below.